right? So, so this is a manufacturing technique for composite. The filament winding is one of the oldest one, but most the valuable thing even these days. So it is well automated now, but very expensive. So most of combustion material machines, related machines, are very expensive. But this one is very well established and well developed now. The filament winding is we say cutting edge technique because it's fully automated, and so it's now it's revolutionizing the production, the high strength, lightweight structure, especially for aircraft and the sports goods. So this is just some of the sample or pictures in real industry. So you can see so this is the machine, empty machine, and it has barrels. Okay? This is winded around the cylinder. And this kind of, this is in the process, okay? Not fully winding yet. And this is also. So this kind of winding machine is very useful these days and well advanced. To use those kind of winding machine, so firstly fiber preparation is the starting point. In fiber preparation, usually it's, as you see, it use continuous fiber, not the chopped fiber or something like that. So continuous fiber implemented with resin and it's wound onto rotating machine, rotating a mandrel. Mandrel is rotating all the way. And winding process, and so its fiber is placed on the mandrel, and the process is controlled by computer for accuracy. So it's winding angle and winding speed and the tension in the fiber, is everything should be very carefully controlled. So it is very difficult manually, because in the case the constant tension is not possible. It means in the real use, in the case, you will get unwanted residual stress. So it's very the unwanted situation. So, so after winding process, curing is needed. Curing is in the oven or in that curing process means heat treated. Okay? It's, during heat treatment, this wound the product is solidified. So it is a final product stage. So key components of filament winding. So in the machine, so fiber delivery system is needed, resin bath needed, mandrel needed, carriage needed. So instantly you can understand already. So why the delivery system, what kind of function must be done by that system, and the resin bath also that is needed to impregnate the fibers before wounding, and mandrel is just a base to be wound, and carriage is because that machine head must move through by using carriage. Okay, and the filament winding pattern is three the typical patterns are used. The four cylindrical mandrel, the helical wounding because it has some fixed angle or winding that's needed. So helical winding or the hoop winding. It's like the waist belt. So hoop winding case, and if it is not cylindrical shape, it's a spherical shape, something like that, in the case of polar winding technique is needed. So those can be controlled from the control panel. And material selection for filament winding, usually we typically use three different ones. Those are not limited for use, but this is very the typical ones. The glass fiber, carbon fiber, and aramid fiber. So I have not seen this fiber from my experience, but I can find this one from the documentation. So it is some of plastic resin type and corrosion resistant types application. Yes. But what I seen so far is that these three different kinds of fiber type I have. So also the pressure vessel is most common use for filament winding process, because the pressure vessel is mostly cylindrical shape, okay? And the end cap is hemisphere. That means the filament winding is very useful for those structure shape, and it's the filament, the fiber tension should be very uniform, right? Very uniform, to keep right circle or such like that, because the inside the pressure should be borne. And carbon type is usually used for aerospace components, and the resin type is polyester is needed. So epoxy, polyester, or vinyl ester, those kind of things match with aramid, carbon, glass, respectively. Right? So the reason the aramid is used for automotive drive shaft, because it is very strong to impact. So it is highly impact resistant. So aramid fiber is used for the automotive drive shaft. And the process parameters and the optimization. So usually we can control temperature and the winding speed and the fiber tension and the winding angle, as you expect. Okay? And the quality control and inspection is needed. So once so you're operating the machine, then from the final product, you should visual inspection first, and non-destructive testing is mandatorily engaged. And this ultrasonic X-ray inspection is used to find internal flaws, if any, and ensure structural integrity without damaging the part. It must be checked. And mechanical testing is also engaged. The strength stiffness test on samples. So that means the whole, the finally wounded one cannot be mechanical tested in the case it is used. So when they manufacture the winding product, so every lot they make different the test specimens based on the same combinations. So every time they check the mechanical testing result is a successful the mechanical properties displayed or not, that they should check that. And the dimensional analysis means the geometry part. It must be precisely the manufactured in dimensions. because it should be assembled with other parts. And mostly this expensive structure used for aerospace engineering. So it's very large scale, and its dimension must be very tightly equipped. And application of filament wound composite is aerospace, sports equipment, energy, and the infrastructure. So if it is tubular type body, in the case it will be chosen for filament wound composite type. Okay? And except that kind of filament winding method, there are other techniques to manufacture FRP composite, FRP fiber reinforced polymers, or fiber reinforced plastics, you can say like that. And the typically we can say the hand layup method and the vacuum assisted resin infusion, we say is VARI. And the resin transfer molding is RTM, and the compression molding method is those kind of, in this category SMC is usually used. So firstly, let's see, the hand layer method is very simple one, very the old method, very the directly understandable one, right? So this any kinds of fiber mat is prepared, and this the gray one, dark gray one is mold. Is mold on the mold. The resin film and the gel coat is the dotted, and so you stack the carbon, in this case carbon fiber mat, or other case glass mat, any kinds of mat prepared is stacked as desired. Okay? And after stacking, the hand roller, by using hand roller, you load the pressure the evenly along the surface of stacked the mat. This is very simply understood, but RTM process is a little bit complicated, but this is also one of very traditional one these days. Okay? So because these days RTM itself is not widely used, because it's that traditional method is these days modified, slightly modified. Because the resin transfer molding process, this one, as you see, it need the mold, upper mold and lower mold, both of those. Okay? That means the upper mold and the lower mold, so it can be used to manufacture small size of parts only. It is not fit for the large size structure. But these days, the EV car, the electric vehicle, or aircraft, or other the civil structure, basically a large part need to be processed. So this one, as it is difficult to use, okay? And it's the productivity, manufacturing rate is relatively slow. So, but this is good to study to understand for to get more the development of advanced ones based on this one. So as you see, this process have the upper. This is upper mold and the lower mold, and the upper mold it must have an inlet for resin and the outlet. The outlet is for overflowing resin, is coming out of during process. And the pump needed and the mixing chamber means this is the molten resin is here, and by pump it can be pressurized inject into this die, this mold. So after the cavity is filled by molten resin, and heat curing is needed. So of course, before the resin, the injection need to get a fiber preform inside. Okay, so before the injecting resin, the fiber preform must be placed into the cavity. Okay, so that means this cavity is not empty ones. There is very complicated fabrics already inside. That means that the molten resin, it has a viscosity. So it is very difficult to infiltrate into that. Okay? So that means you need a high pressure to inject the molten the resin into. Okay? And once it's filled, then heat curing is needed. Okay? And after heat curing, it's ejected. So you can get one product here. Because this RTM is one of traditional technique already, and as I said, it is become the very basic method for advanced ones. So if you consider seriously the development of any composite system by yourself, in that case, strongly recommend you to build the RTM setup in your lab too. It is not so expensive. It can be built very easily. Okay? So this is one of the built setup. So the power controller is even Arduino can do these days. So Arduino very cheap, right? And but this is not from Arduino, but you can use Arduino these days. And this is the mold. This is mold, as you can see. And the heating pipe is needed because you need heat treatment, right? And heating coil also needed. Right? It's very easy to install. And pressure bin also needed. And the pressure inlet, this is pressure inlet. Pressure is used to push the molten resin inside. Right? For the resin, you need two different kinds of can. One is catalyst, another one is resin itself. So it should be mixed before injected into the cavity. So schematically, you can summarize like this. Resin transfer mold process is if we think of full cycle from the raw material. So its layup is needed. This is kind of preform, right? So preform tool, this preform tool is to fit into the mold. So cavity will capture the layer up to fibers. So this is fiber form, the fiber preform. It's put into the cavity, and the resin infiltration is started, and the curing and opening for final product. That means in this case, it's just you can see how the much time is needed to each step as a sample. So the transfer preform into mold 10 seconds in this case, This mold closing and the resin injection is 30 to 40 seconds. Curing is 120 to 9 or 9 seconds or something like that. Okay, so that means 120 seconds at 120 degree, and the 9 after that the 90 seconds at 130 degrees. This kind of schedule must be designed by yourself. So choose the time, heat treatment time, and the temperature. It's not just 2 steps. You can use 3 steps, 4 steps, and any kind of step is possible, according to your understanding, the fiber and the matrix system required. So it is the manufacturing the what to say. It's not the secret, but to that company it can be the very valuable information. Okay, because it decides the quality of their product. Okay? This is very important step, and from this step you can decide the quality of interface between fiber foam and matrix. So this kind of schedule needs to be trial and error many times before set your process finally. And after curing, so injection, opening and the injection stage, about 10 seconds total. So 150 to 180. 180 second total time is needed. That means one cycle at one product. That is productivity, and can decide the price of the product. So this kind of whole schedule means we say is a manufacturing process cycle. So that is RTM, and many of university laboratory have that kind of self-built designed RTM to make specimens for their new systems and get to know the effect of heat treatment schedules, so that they can write papers and compare with their computations. So to develop your own product, it is not possible without understanding RTM process and how to calculate the process simulation, through simulation. So that kind of RTM is most limited the comment is it cannot make a large scale structure. It can only possible for small scale. So and very slow, relatively slow cycle. So these days, this vacuum assistant RTM is most vastly required process. Even 2 or 3 years ago, I had participated in simulation for VARTM on the product by the Boeing, and because before VARTM, they usually use autoclave method to make their product, but it is very expensive process and the productivity is relatively low. So they wanted to get their product from their product by this VARTM, because this is very relatively cheap process, and each cycle, the production cycle is very short. and it's very easy to use for large scale structure. But there is only one problem. That problem is actually the dimension is very difficult. The final dimension is very difficult. So in order to make the finally accurate dimension, the company that provide the manufacture the product for Boeing or Airbus, they need to show their ability. They can get final accurate dimension through VARTM. At those days they claimed although you can make the product by your autoclave. In that case, I will not buy your product. It is the Boeing or Airbus claimed to the companies they manufacture their products. Why? Because in the end they need well-established the manufacturing process for their companies. So even though they can make the same product by a different method, in that case it cannot be standardized. So they need to have any standard method, common method from the companies that the manufacture Boeing or Airbus large-scare composite panels. So the VARTM is a mix two traditional methods. One is open mold, so hand layer you saw. Usually that kind of open mold method was used to build the hull of a ship. It's a very traditional method. So they have a very there is no limit to make the large scale hull of a ship by using open mold. So the large scale the product is possible by using the open mold. And another one is RTM. RTM is used. So both technique was confused into one. That is VARTM. So VARTM process means one-sided mold. There is no upper mold. Only lower mold is needed. That is open mold. And the dry fiber reinforcement, preform, is used. And that means it is very easy to be placed on the mold. And the vacuum bag will be used to seal the preform against the mold. That acts like upper mold. The vacuum bag acts like upper mold. And the resin injection under vacuum pressure. That means atmospheric pressure will be acted like pressure air from pump. So pump is not needed because atmospheric pressure will act like that. And the resin injection under vacuum pressure and use of atmospheric pressure of compaction. That is that meaning. Okay? So this kind of RTM process needs to widely simulated by using computer. Okay? That technique one is crucial, needful one, and the practical technique training also very needed because to get accurate dimension as a final product, trial and error is very much needed because during a heat treatment process, the resin will be shrunken. That means the final dimension is not possible to estimate in advance. So after trying to manufacture practically, they can know how much that product will be shrunken. So by trial and error, they can negotiate to get accurate final dimension. And the VA-RTM combines following key benefits. So high part quality and repeatability, similar to RTM, and the flexibility and the scalability, similar to hand layup, and the reduced volatile organic compound emission, and the cost effectiveness for large structure. So this large structure has emphasis for this process. Okay. But this VA-RTM also has some limitation because potential for air leakage and dry spot formation. Dry spot formation means dry spot, the preform, the fiber was not wet. In the case we after the ejected, we say it is dry spots found because there's no resin at all. Okay? And the limited control over fiber volume fraction. So fiber volume fraction cannot be increased to the limit. It cannot be because the pressure difference is just 1 atm, just 1 atm. Okay? And challenge in achieving uniform part thickness. It means there is no upper mold. It means between upper mold and the lower mold in case of RTM, it cannot be embodied here. That means the upper body is a little bit can be different because there is no upper mold. That means the product thickness can be varied. So that is a challenging point. So this is a kind of the schematic. So this kind of shape is VA-RTM. This pink line means vacuum pack, and this blue one is a molten resin. And there is the resin inlet here. This is a resin outlet here, and so there's the vacuum pump is needed to make the vacuum condition inside the vacuum bag. Okay? So, and the outer vacuum bag, there is only the atmospheric pressure. So atmospheric pressure will the compact this the composite material structure. Okay? So that the molten resin should propagate, infiltrate like this kind of shape. Okay? This kind of shape is. So the process about the hand layup and the RTM and the autoclave, it does have some comparing points compared to VA-RTM. So VA-RTM has the advantages over hand layup. Its VA-RTM is a more cleaner process and better part quality possible, and higher fiber volume fraction. But compared to hand layup, this VA-RTM must have a higher initial tooling cost, and more complex setup is not possible for a VA-RTM compared to hand layup. In the RTM case, over RTM, VA-RTM has advantages over about lower tooling cost because it has no upper mold and the ability to produce a larger part. and more flexible mold design is possible because there's no upper mold. And the limitation compared to RTM is a lower injection pressure because just one ATM is used, and the potential for dry spot because this can be happened due to small compaction pressure. And over autoclave, so VARTM has advantages, the lower equipment cost. So autoclave is very, very expensive equipment. And the ability to produce a larger part. Autoclave also used for curing larger part. But the VARTM case is much cheaper, or facility can be used for that. And the limitation of autoclave is a VARTM is a lower maximum fiber volume fraction because compaction pressure is low, and the potential for thickness variation is this is inherent weakness. Okay? So VARTM can be said is one of most needful technique these days. So the large scale composite material, the manufacturing company is use either filament winding or VARTM. So that is the case of large structure or composite panel manufacturers. So the VARTM, if you understand the fundamentals of VARTM, in that case you can understand the better control and process optimization. And as a result, you can improve part quality and fewer manufacturing defects because the differently from RTM or hand rail or autoclave, this VARTM has many variations, thickness variation or dimensioning, the variation, something like this. So that means more trial and error is needed without good experience in advance or the simulation. So if you can use a simulation, that means you can know the rough optimization point in advance. So from that spot, you can reduce the number of trial and error of VARTM practice. Right? That means it can save your time and it can save your money. Right? So the key physical phenomena for VARTM process is resin flow phenomena and fiber preform compaction and the resin viscosity and the composite curing behavior. These four subjects should be understood to use VARTM manufacturing technique for your product. Okay? So resin flow phenomena, that is about fluid flow through porous medium. And the fiber preform compaction is about affecting the final part quality and the fiber volume fraction. Right? And resin viscosity is about affecting flow behavior and the filling time. And the composite curing behavior is complex heat transfer and chemical reaction. So these four subjects should be calculated in advance by using computer. So, I just give very basic fundamental equation. It is not. I have no intention you have to study this equation, but there are some commercial packages to simulate this kind of things. But behind that computer the graphic user interface, this kind of equations are included. So you can to check any kind of documentation if you wanted to have any intention to study more deeply, it's a 1/4 or 1/4 subject. Right? So, for example, raging flow phenomena. So, just two kind of equations. The related theories needed. One is Darcy law. So we say Darcy law is a kind of a flow into porous medium. Okay? So this is these are related the equation, and also continuity equation is needed to consider. And where RTM so in the viewpoint of raging flow, so it has key aspect is through thickness flow, and flow tracking and the dual or scale flow. These three minor subjects included. The through thickness flow is the primary direction of raging flow is through the thickness of the preform, and facilitated by flow distribution medium. So you can see the later. Okay? And follow tracking means the raging may flow faster along edge or channel, resulting in uneven filling. And the dual scale flow means the raging flow occurs between fiber bundle and within fiber bundles. That means between fiber bundles means we say it is macro flow, and within fiber bundles micro flow. So one bundle means 1K, 2K, or 10K. We say like that. 1K means one bundle. 1K bundle means 1,000 fiber. So the binding in one bundle. So 12K means one. So 12K means so 12,000 fibers are bundled. So those kind of terminologies used. And about fiber preform compaction, so we use two different models. So this is very famous models in this field. So Gutovsky model and these two models is usually used for computational programming inside. Okay? So effect of compaction is concerned about the preform thickness, porosity, and permeability. Okay? And the resin viscosity. The resin viscosity we use this kind of model. And this resin viscosity is considered temperature control and part life of a resin system, and viscosity change during cure. And the curing behavior of composite material, so we are using this energy balance equation and kinetics and this curing. So this kind of equations the programmed into commercial packaging. So you can use chemical reaction or any heat treatment or fluid flow, viscous flow, those kind of things you don't need to understand in detail, but those kind of things are already programmed into commercial packages, so that if you just understand the stories of each subject, then it can make you use more usefully the commercialized packaging. So this is composite pure vacuum systems components. So there are many terminologies here. So this kinds of terminology is needed to you understand, because to use the commercial package, they ask that kind of terminology as a parameter. So you should say the radio controlled aircraft fuselage, the open mode shape. This looks very messy, not so neat like schematic. But this kind of open mold hand up, it's very, it looks like the VRTM, so low mold. So VM RTM process setup and procedure can be the simplified like this. So air compressor is needed, and electric scale is needed, vacuum pump needed, gas container needed. So these four the equipment around the manufacturing bed. The inside the bed, there is a lower mold here, and there are many fiber preforms here, and there's this green one means need fill ply. This is one of element used for VRTM, and this vacuum bag. This vacuum bag is pink color, and the sealant tape is this is used as a bumper, right? And the preform, the carbon fiber is preform and valve. So you can understand what kind of measurements in this. Pressure is monitored, okay? And temperature should be monitored, and this valve will be controlled from outside. Okay? So this glass window is needed because you need to look into the product during process, during manufacturing. So the simulation means all of the materials included inside the manufacturing bed is needed to include. So vacuum bag, fill ply, this tape, pipeline, not this pipeline, the carbon fiber. Those kind of mechanical properties, depending on temperature, should be known in advance. So those kind of temperature dependent mechanical properties can be obtained from supply. But if you don't know what kind of mechanical property needed, in the case you cannot ask them what you need. So if you have some special composite system in mind, then you need to focus to get what kind of things with mechanical properties you need, something like that. Then the parameters will be supplied from outside if you ask. Okay? So otherwise, you must use kind of default parameter properties provided by computer package company, but it is not accurate. It cannot be used for evaluating your manufacturing process. It cannot. So it is just for exercise. So meaningless. So you must get real properties to use that commercial process. So, and the key consideration of VRTM, so in summary, is a preform compaction, and the flow front control, and the temperature management, vacuum integrity, resin bleeding, post-cure. Those kind of consideration must be concerned. Okay? So each of those, I believe you can quickly understand what those are, right? So preform compaction is preform compaction means that preform, you have a stack of carbon fiber, for example. It needs to be preformed. But if you use too much the strong compaction pressure, that means that preform will get pre-damaged. It is not wanted, right? So if, for example, if you give too much the compression, then locally there will be locally buckling can be found. And that buckled mostly can be recovered after removal of that convection pressure, but during buckling, it can leave in permanent breakage in fibers. So it will be the micro defect after manufacturing as it is. So don't neglect the optimal compaction pressure. And the flow front control means it monitor resin flow front and adjust the injection as needed to prevent dry spots or racing tracking. It means resin flow. Resin must be flow from the one side. From our previous schematic, it must start from left upper corner. So that point is a starting point. And during the resin infiltration, that the front, the flow front will move right and downward. So if the speed is not well controlled, then it's too slow or too fast. In the case, there will be some unfilled space, or according to that space size is a macro size void or micro size air trap will be found. So it will be the final defect. So it cannot be used as product. So that is flow front control. And the temperature management is resin viscosity must be well taken care of. So viscosity, liquid viscosity severely depending on temperature. So if manufacturing temperature is different from local to local, that means each part of viscosity flow characteristic will be different. That means filling rate will be different. That means it's the filling status will be different. That means your final product will have inhomogeneous inhomogeneous properties will be displayed. So it is uneven property local to local. So it cannot be used. So according to the local temperature, you should try to keep the temperature as constant. So if it is very small product, then it's very simple to keep the constant temperature. But why we need VARTM? Because these days most of compressor structure has a large scale. It's 3 meter or 5 meter long or sometimes 10 meter or larger. That is a very long distance in manufacturing process. So it is not inside the insulated the space. It is open space. So how you can keep that temperature constant? It's very difficult. So UV is not enough to use. I mean any kind of technique to keep temperature, heating or cooling is needed to keep this optimal condition. And vacuum integrity, vacuum, continuously monitor vacuum pressure and address any leak immediately. That means vacuum pressure is, so there's a compaction, the compaction pressure is only atm, 1 atm. So if inside the vacuum is not complete, that means compaction pressure will be diminished. So it will be the different situation we expect. Right? And the resin bleeding. So resin bleeding is some extra resin should the leak out, bleed out. Otherwise, it will make richy, the epoxy richy zones of the inside. So it will give the very weak structural zone. Yeah, so it must be careful. And the post-cure is depending on the resin system. Post-cure cycle is needed to achieve optimal mechanical properties. So mechanical properties decided finally after heat treatment. So depending on the characteristic of based on the same the material combination, the final mechanical properties are very different. So that is about VARTM. So now you can say about just conceptually vacuum-assisted composite manufacturing techniques. This VARTM is one of those. Right? So this vacuum-assisted composite manufacturing. So first step is preparation. Now you understand what is preparation in this place. Okay? So layup, okay? Dry fiber layup, because need to make a preform. Okay? That is first stage. And bagging. Bagging means vacuum bag bagging. Right? It's needed for this kind of vacuum assisted one. So bagging is needed to sealing the layup with a vacuum bag and the tacky tape is needed. And the installation of a resin inlet and the vacuum port. Okay. Now you easily understand why there is resin inlet is needed and the vacuum port needed. It's a vacuum assisted manufacturing technique. It's a mandatory needed, right? It's a very basic thing. And the infusion is a need resin into the preform. So infusion means drawing resin through layup using vacuum pressure, and ensuring complete without fibers. And the last stage is curing. Curing is heat treatment. Okay? So allowing resin to cure on the vacuum, the demolding and post-curing is necessary. That is a general stages needed for vacuum-assisted composite manufacturing. And this kind of techniques advantage is it can enjoy. It can provide higher quality as a result. So reduced void air traps and improved fiber to resin ratio, the enhanced mechanical property and the surface finish will be possible. And the cost effectiveness, because it has no upper mold. And so that means the pump is not needed. So, differently from the RTM. So lower material waste and labor cost. Yes, of course, it can be obtained and suitable for producing large and complex parts efficiently. So it's advantage from hand layup and the RTM. So both advantages can be used for the vacuum-assisted composite manufacturing. The versatility is compatible with various resin systems and reinforcement adaptable to different part size geometry. is very fit to those kind of structure. So vacuum assisted process has key components. So for as a the manufacturing method is vacuum pump. So vacuum is mandatorily needed, right? And flow media facilitate even resin distribution across the part. It is a complete fiber weight. This flow media means it is a kind of the kind of molten resin flow or channel kind of. It can easily transport a molten resin over the preform, so it can accelerate the molten resin transport. And the resin trap prevents excess resin from entering the vacuum pump. So protect equipment from damage. Vacuum bag is needed. Okay. And the mold and layup preparing. So mold preparation for this manufacturing technique is mold preparation must clean. This mold is lower mold because there is no upper mold. So clean and apply release agent. Release agent is after the finish, after curing finish, it should be easily ejected. So that need release agent is needed to adopt over mold. They ensure smooth surface for quality part finish, because mold surface condition can decide the surface of a product. And the fiber placement is this place the preform on the lower mold part. So cut and position reinforcement of fabric, and follow designed ply the schedule for optimal strength. Okay, about preform preparation. And then auxiliary materials needed, peel ply, flow media, and breather. So over those kind of the sheets should be placed over preform to help the resin flow. And the bagging and the sealing is very important, because this is a vacuum assistant. So if there is the bad sealing, in the case the process of fully the failed, right? So vacuum bag placement is the drag back over layup and avoid the wrinkle to prevent resin leach areas. And the sealing technique is advised, and the port installation and the leak check is mandatory before starting this process. Okay. And vacuum and resin infusion. There's a vacuum application and the resin preparation, infusion start, and the flow monitoring. Each of the content should be applied for this manufacturing technique, especially with very special caution, because vacuum application indicates gradually increase vacuum pressure. Monitor for any back movement or distortion. So because to avoid any damage or unwanted shape from vacuum bag. And the resin preparation is a mixed resin and hardener thoroughly. The well mixed is needed. Okay? And degas if necessary to remove air bubbles. Okay? So the reason this kind of the application cautions listed, because in practice this kind of application frequently leave many damages or defects just after manufacturing. So each application part must be checked if you train or exercise this RTM like a manufacturing technique. So and infusion start. So open resin inlet valve slowly. So observe resin flow front for even distance. This is a very common sense, but we don't know how slowly the valve should be open, it closes, something like that. But that means any kind of the abrupt application of open or close or pressurization or vacuuming will make a permanent damage on your product of the ejected. So those kind of things is very common sense like, but it must be cautioned. And the flow monitoring is adjust the inlet pressure as needed. That means flow must be fit must be appropriate to the make preform fibers wet completely. If it is unwet partially, that means the total structure will be the failed output. Means this VRTM is usually used for large scale structure. So that means one failure of manufacturing, that means big time consuming and big cost lost must be expected. So you should very carefully the practice this kind of things. And curing and composite part, initial cure, temperature lamp, cure hold, cool down. So you can read this slide after this, because you can get I guess download this slide for your use. From this slide you can get more documentation with the same terminal or something like that. But this can be used as just a note for you. Right? And the consideration for part design optimization, geometry, resin flow, ply schedule, and cure profile, and the troubleshooting common issue. The dry spot, resin leach area, vacuum leak, premature gelation. This kind of issue is very common, commonly encountered issue during vacuum assisted composite manufacturing. So if you got dry spot, then the common cause of dry spot is poor resin flow. So how to solve that problem is adjust the flow media layout. And the resin leach area found, then it means maybe excessive resin pooling. So to resolve this problem, so optimize the vacuum pressure. It must be controlled. And the vacuum leaks issue, the improper sealing is the cause. So double check back end connection. And premature gelation found, then incorrect mix ratio caused it, and solution is verify resin and hardener or measurements. Okay, those kind of the common the issues can be treated, and that is about vacuum assisted composite manufacturing technique. So it is not automated. It is not automated. So VARTM also to preparation of manufacturing process, all of steps you should prepare by yourself. That means much manual job needed. So it cannot be the fully automated. So so that's why still it is not fit for mass production part. But very special and a small number of productions, those kind of case, it can be advised. But recently, so most of the applications needed to be lightweighted, but keeping its structural strength kept. So it is very difficult to be achieved based on conventional materials. So although composite material is very expensive, many cases the using composite materials is the only one solution to get a final product, to meet the requirement. That means we must overcome the cost issue. Okay? So it is not possible for all kinds of composite system, but if possible, we want to replace manual work by machine, automatic machine. So these days, the advent of robotics development. So we can build very sophisticated manufacturing robot even for composite materials. So this kind of manufacturing machine for composite material manufacturing, it is also initial stage, not a fully developed market yet. That means there are possible automatic machine for composite materials, but still very, very expensive. So small and medium company cannot use it. It's impossible. Only very limited number of the multinational company can use it if needed. Okay. So, but it's very surprising for me to see so many automated composite material manufacturing machine is introduced in the market very rapidly. So I think maybe in India, I think because in India there is I think most of, for example, manufacturers in automotives, for example, can be found in India. And for automotive makers, this kind of composite material component is just beginning stage to be introduced. And what it is to the automotive manufacturer, I think mass production is their basic principle, differently from the the airplane manufacturers. That means automated machine for composite material will be very much needful, like India or China, something like that. So if you can combine the recent robotics and automated machine for composite material, then you can contribute greatly to automotive part industries and for other application manufacturing companies. So, in that sense, it is meaningful to introduce about automated tape laying machine for composite material first. So that's why I chose this topic as one of the subject today. So there are the ATLs. ATL is automated tape laying. Here is a tape means a composite tape, that film. Kind of prepreg. So definition, the ATL is computer controlled process for laying pigmented composite tapes. And it precisely places tapes on a mold surface to create complex structure. So placing films, fiber preforms on mold surface was traditionally man's manual work. But now it is tried by using automatic machine. That is ATL. Its efficiency is significantly reduce labor and improve consistency because it is that work is done by automatic machine. So it should be very accurate compared to humans' manual work. So its consistency is greatly improved by using ATL. And it is very ideal for large and relatively flat or slightly curved components. This is the limitation of this machine at this time. Because if it has very complicated curved surface, that means automation is very difficult, not easy. So it is not overcome yet. But if it is very flat and very gradual or curved one, then it can be work done by automatic machine. So that means these days ATL is a very the flat-like structure only, not so curved one, complicated one. And the precision, the ATL machine's precision is it can achieve tighter tolerance because it is machine. And the excellent fiber alignment, of course, it can be expected. Crucial for aerospace application requiring high structural integrity, because this is not possible for automotive part yet, because automotive part is small and the surface the geometry very complicated, so it is not possible. But for airplane, its body is very large cylinder, or its wings are very flat, so it's very useful. But that is dilemma for this machine, because how many airplanes will be manufactured 1 year? It's a very small number. But this ATL machine is very, very expensive. You can see this right-hand side, this one is one of ATLs. These are also ATL machines. So this is not millions or million dollars, not $1 million. It's tens or hundreds of $1 million. So who can install this kind of machine into the industry to manufacture small number of parts? Okay. Anyway, so So this is the already found on the market. Okay. So it has very flat mold and very very large radius curvature and so on, right? And the ATL process flow is very similar to hand layup. And the first material preparation by machine. Okay. So the machine can pre-impregnated tape can be loaded onto the ATL machine automatically, and the material is carefully handled to maintain quality, of course. And the tape placement, the machine had precisely laid tape onto the mold surface, and it follow a pre-programmed path for accurate placement. And the compaction is it use roller, that robot hand. The roller on the robot hand applies pressure to ensure proper adhesion. In hand layup, that kind of plate, and we use the hand roller. But now that the robot hand use the big roller. So its compaction pressure is very, very accurate. Right? So this compaction, so as a result of this compaction now, it can remove air pocket. And the surface very ensure the good quality consolidation. So, and the cutting and restart is very quick and accurate. The tape should be cut. In the hand layup, we use knife by manual. So, but machine use is the machine knife, machine seizure sometimes, and at the end of each pass, and the machine then repositions for the next layer. It's automatically. So, key component of ATL system is a robot arm, and tape feeding system, and the cutting mechanism, and the control system. So all of these kind of things can be possible for only these days, not 10 years ago, 20 years ago. And as I said, still it has a big limitation. Only the flat surface only. But maybe the robotics, maybe it can be introduced on commercial market sooner or later after new robotic industrial period will become. So every expert expect like that, because these days there is only small number of industrial robots can be possible, scalar robot, something like that. But humanoid type robot is about to be on the market now in 2 years. That means in 2 or 3 years, the humanoid type robots can be used for this kind of automatic composite material manufacturing machine. In the case, very complicated the surface can be treated. And then what you can expect, then composite component parts will be commonly used for every kind of machine, automotives, mobilities, structures. So it will be very different. The period will come, I think. So robotic arm has provided precise movement and the positioning of tape laying head. So these days only very simple work is replaced by this robot arm. in the case of composite material manufacturing area. And the tape feeding system is easily can be expected. And the cutting mechanism and the control system. So even this kind of the simple works, that ATL is very expensive and less the complicated work compared to human hand job. So, this is very open field, I think. So material type for ATL is used basically carbon fiber prepreger, the glass fiber prepreger, and the aramid fiber of prepreger. Okay. So now you easily know the carbon fiber and the glass fiber, aramid fiber, the differences between them. Right? And each advantage also you now the well grasping. Right? So advantage is a carbon fiber, high strength, lightweight. Glass fiber cost is relatively low, the cost effective, but and very good the thermal insulation and electrical insulation. And aramid fiber is impact resistant exclusively, right? And the vibration and the damping characteristic. So this kind of fibers we reviewed in the lesson. So those kind of fiber is very commonly used for advanced composite. Yes. So even for ATL, so carbon fiber prepreger, glass fiber prepreger, aramid fiber prepreger is used for carbon fiber case, aerospace structure, high performance automotive. And the glass fiber is marine or wind energy blades. And aramid fiber is polyester protection aerospace interiors. So glass fiber prepreger is relatively heavy. It has the low strength, low specific weight. Comparatively, it used for ground structure or the ocean structure. So optimizing ATL parameters as a layup speed and the compaction pressure and the temperature control, tape tension is the same as the parameters you have seen in the VRTM or hand layup process. So applying to the same, right? So this can be more accurately controllable through ATM. And the quality control was very automatic. In-process monitoring is possible through various sensors, and non-destructive testing is on-site is possible, and the dimensional accuracy is possible. And the sustainability and the future trend in ATL is a recycled material, AI integration, multi-material layup is expected, because all of those ones is focused on the eco-friendly environment requirement from society, and if we adopt AI integration together with ATL, that means more sophisticated, complex surface can be handled. So it's a very understandable trend. That means that motion will be very the interdisciplinary fusion area. And the introduction to the automated fiber placement. So this is also the similar but a little bit different automatic machine. So fiber placement, automated process, complex geometry, this can be used by automation. So this is a kind of the AFP, the machines. So this is some of those are just for fiber placement only. So it can work on a little bit more complicated surface, differently from the ATM. And the key component of AFP system of fiber delivery and placement head motion system is similar to ATM. And the advantage of AFP over manual layup, enhanced precision can be enjoyed, and increased productivity, and reduced waste, and improved consistency. It's similar to the ATM, right? And the material used AFP manufacturing is carbon fiber used, glass fiber used, thermoplastic, and prepreg tapes. All of those can be possible for existing machines. And the layup strategy and optimization, fiber orientation, layup sequence, compaction force can be controlled automatically by the AFP machine. So inspection and quality control in AFP in situ monitoring is possible, and the dimensional inspection also possible. Destructive testing is on-site possible. Right? And the challenge and the limitation of AFP is complex geometry. So still it has some limitation, like HL, and the defect avoidance and the material limitation and the high initial cost. Still, the said their limitations. And the AFP technology, the future trend is intelligent automation also being tried, and the digital twin is also used together, and sustainable materials are required. So among that, digital twins means digital twin is creating virtual simulation of AFP process to prevent defect before production. That means currently the machine is just controlled by a program, but that means a computational model will be collaborating with this machine. In the case, before operating this machine, the digital twin means a computer model used to predict the result of manufacturing in advance. So before trial, some kind of parameters can be controlled in advance. So it can save time and money. Right? So application in composite manufacturing is aerospace, automotive, wind energy, and sports equipment already. Yeah. So this is about the manufacturing techniques. So this is just a part of all manufacturing methods, because all of those cannot be discussed here. But today I focused just three the crucial ones. One is RTM, another one is VA RTM, the last one is fully automated machines, three of those. Those are the currently commonly used ones. Have any question about this? It's a little bit cold here. Okay. So interesting one is so if you understand the composite system and composite system first, then after that you got to start thinking how it can be manufactured, how it can be made. The manufacture means like some industrial or the terminology, but you can think just this small patch of that composite system. How I can make this composite. So you can try by yourself. You can use oven, electrical oven, small electrical oven to heat treatment by yourself. You can check 2 or 3 cases sufficient. Then you gotta know what kind of different result can be obtained after this heat treatment, that one. Okay. So overall temperature can be known, although it is not accurate. It can be checked from the documentation already. So once you can experience any kind of composite manufacturing by yourself, in that case, it is a very good start point to design your own machine. And it is very good. In that case, it can be named separately. So you can think how many different manufacturing methods can be found these days. So once you know the other patented manufacturing technique, understand those, it is nothing. It's nothing. It's very natural. If it was your case, you could do like that also, but it's already patented. But there are so many different ways. It's open ways to develop new manufacturing technique by yourself. That it must be rooted on special composite system. Because different composite system require different manufacturing technique. Okay? So the most important thing is to understand the composite material system. Before that, where you want to apply that system. The part structure you want to have. To find that part is first mission. After that, rather than just a traditional material, if you want to make it by your composite material, then you can check what the system is possible, fiber, sometimes carbon fiber, then you can use your hair. You can use hair. It's very nice fiber. It's very nice fiber. It's just 50 micron in diameter. Okay, so it's so very nice. Maybe you have a very smooth hair, then your hair diameter may be less than 30 micron. It is very expensive advanced fiber already. That's natural fiber. Natural fiber. So you can don't use your friend's hair. Use your hair. So it's very interesting. Interesting thing if you try like that. You can be the composite material expert sooner or later. Okay. Yeah.
Automatic three-plane method, is it possible to achieve higher fiber percentage, higher volume fraction?
Yes. The ATL or those kind of machines can achieve the highest the volume fraction. But the VA RTM, it's not possible. VA RTM or hand layup is not possible. But RTM is possible. So it is because compaction pressure and the temperature, temperature control is the issue, key issue to achieve a higher volume fraction. Because it must be well compact, and the resin should be well molten, and so that the all of the fiber must be completely wet. But by using VARTM or hand layup, it is not possible. It has a limitation. But if it is through the machine, automated machine, it is you can control every parameter very precisely.
And what about the bonding between the layers? So we are using ATL or AFP?
So adhesive or the polymer can be used. So you mean the between ply? Between ply. It's a conventional adhesive. So you know the paste. So not the paper paste. Okay. There are many industrial paste. It can be used.
And sir, we are discussing about the only thermoset regimes.
Thermosetting?
Manufacturing of composite using thermoset.
Yeah, thermoset is mostly used. Yeah.
What about thermoplastic?
Thermoplastic also can be used, but the thermoplastic case its use is mostly low temperature, not the high temperature. So thermosetting is a little bit more solid at elevated temperature, even polymer, right? Because it's cross-linked. So mostly epoxy resin is used, and the polyester is used. Not vinyl is not used for, vinyl is thermoplastic, right? Because it is not rarely used for automated machine resin. So mostly.
Can we use these methods for the thermoplastic as well?
I think so. Why not? Why you do you think thermoplastic is difficult to be used by?
Because in general we used to get the thermoplastic in the solid form, like the granules or powder form. So it will be difficult with.
But I think if that thermoplastic is made as a layer form, as a tape shape, for example. Not you just think about plastic molding. In the case of powder is the material, but if it is made like a tape, pre-prepared shape, in the case it can be used for ATM machines. In the sense. So I mean the intermediate level of thermoplastic, not the raw material level thermoplastic. It is powder. It's not used for the automated machines because it is kind of plastic molding, plastic injection process. Even composite, if you wanted to use those kind of this, you can do. But in the case, there are many void trapped inside, so no one wanted to use like that because there are many fiber preformed inside, and the powder must be molded into that cavity. It's very difficult to get fiber wet. That means after all there's many void, so the product will not be good shapes. In the sense, it's not good so forth. So this is lecture 9, and so quickly finish it. This second one. So this is the process modeling story, process modeling. So previously we discussed about the practical or composite material manufacturing ones. It is a real stuff, real material. But before the manufacturing, we can simulate based on a model. So just to talk the simple story as an introduction. So process modeling, of course, it is very important. If it can be used, it can be used. But fortunately, you can find some commercialized packages to simulate composite manufacturing. Okay? So I just introduce very few ones here. So this is the part size and the cycle time for the composite material structure. Means if this kind of compression molding ones, maybe so without simulation, it's not so much difficult. Because without simulation, because compression molding case, within few minutes, it's a cycle time. So you can make the many trial and error to find the optimal condition for your final mass production. But if come to the some hours for manufacturing cycle time, RTM, maybe I don't think you can have much patience to conduct multiple number of trial and error. If you can find some reasonable or optimal parameter combination before starting your trial and error, in that case, you will be willing to run program. Right? So, but it's shift. Shift means half days or something like that. Or maybe I wanted to run computer model days. Of course I will. I don't want to try an error for 10 times again, 20 times again to find the optimal point. I will not. Weeks as a vacuum infusion preparation. It's usually used for large scale ones. That this is not cow, the cow size, cow size, not truck size, right? So wind blade size. That means this is about 100 meters. So if it is a large scale one, usually the vacuum assistant, the manufacturing technique is suitable. In the case, at least a day to a few weeks to complete one cycle. So I will not conduct the trial and error multiple times. I wanted to avoid that case if I can run the computer models. So composite manufacturing process, you got already understand what's the layup and the molding and the curing, right? And there are two different categories of commercial packages to simulate your model. So one is use general purpose programs. It is not developed, that code is not developed to simulate any special case. This is a general mechanical, the equations can be simulated inside. Actually, they just solve partial differential equations. And all of engineering principles can be formulated into the form of partial differential equations. So that means general purpose programs for fluid flow or structural analysis. Those kind of things can be used to simulate your model too. But in the case of more sophisticated engineering knowledge is needed. Because so how it can be used for your model, you must assemble all of possible fragments by yourself. That means you need some profound knowledge of it, okay, to use in order to use a general purpose. It's Abacus or Star CD or Front, NCS, those kind of things are general purpose programs. It can be used for structural analysis, failure prediction, material optimization, any kind of things can be used even for the composite material manufacturing process. So it can mold filling and the curing, demolding, because curing means it is the viscous thermal fluid flow problem, and the heat transfer problem, and the rheology problem. So those kind of can be done. And the automated fiber placement, these kind of things also. If you want to develop these machines, you can use dynamic related commercial packages like Adams or NC's Dynamics, something like that. Right? And the compression molding also. These kind of things, all of those can be used to run your model. So this is a structural element. So can be the modeled and analyzed, and computational dynamic CFD is from the Front or Star CD or NCS, the multi-scale modeling, Cosmos, optimization algorithm. So there are so many different kinds of commercial packages for general purpose. So those I think you will not want to you will not want to use. Rather than it, you want the special purpose one. If you wanted to run the composite material molding, there are some specialized purpose programs. Those are programmed specially to apply for your problem, your model. Okay? So I have no relation to this Moldex or to other software I am introducing here. I have no relation to those kind of companies. But I just wanted to show that this is not limited. So there are more softwares to be used like this. Okay? For example, this Moldex 3D, this is not so famous one. This is relatively recent one. It's a Taiwanese simulation package. So by using those kind of the special purpose program, you can pre-mold before conducting real manufacturing process. You can make your model. That model is they provide the tool, pre-processor tool, so that you can build your own model easily based on the related terminologies you have learned so far. This calls the two. So based on that, you can be guided to build your model, and you can choose many manufacturing parameters as a preset the number So that in that case, what will be the result after molding? Okay. Then this case, there are some defects. If you set some, this is kind of the experiment, but the virtual experiment. Experiment means if you put one the parameter set, then you will get one case output. If you change your parameter set, then you will get a different output. So you can guess, I want to use this manufacturing parameter. In that case, what will happen? Okay. In this case, put some parameter, then see, there are some defect. There's defect. So this parameter will not be good choice. Okay. You can know. It's a very cheap way. Okay. Very cheap way and a very fast way. So so based on your chosen parameter set, you can see many different kinds of the output. It's a residual stress distribution, or it's a porosity, or crack, or on wet zone. Any kind of output can be checked from your. This is another specialized the software. This is ESI software group in France. So they're PEM composites. So they provide PEM, RTM, and any other different type of VRTM module, RTM module, CRTM. There are many different kinds of composite molding technique can be simulated easily by this. So PEM RTM case, RTM process can be simulated by the simple guided model. So this they compare so some of users they presented the result. Actually, this is from one of Japanese user of this PEM RTM user. After using, he compared his real the manufacturing results and prediction results. He just compared how accurate both. So very accurate. So by using PEM RTM model, this is purely the virtual production, and this is a real production result. So there are preform inside, right? And it is filling. It can be checked. Both is compared. Right? So without this kind of real molding trial, by just by constructing your own model and set your parameter, you can experience in advance what kind of output will be expected, so that you can get virtually optimal parameter sets before conducting your real molding. Okay, so you can save tremendous time and money. Okay, although you must pay for this program use. It's I believe it is about $30,000 per year for use this program. Okay. Anyway, this PEM's composite you can except RTM, VARI is also specially developed, and the CRTM and HPRTM and more. You can find them. And they also provide the many different kinds of usable fiber properties and the matrix properties and its rheological properties depending on temperature. So the optimization of parameters means for example, you need to understand terminology. You choose among the options LCM. So LCM is because you want to simulate RTM process. That means RTM is part of LCM. So that's why, although you have not a background of any mechanical engineering or industrial engineering, even in that case, you must know what is LCM as an article level. So that LCM means RTM, RIM, VA, RI is all over part of LCM. So you should choose LCM to use this program for your RTM model analysis. And the injection pressure or flow rate can be chosen. Temperature cycle you can set. And the location of injection gate you can set. And the vent vacuum port location you can set. If you set different position, you will get different output. Right? And the curing cycle also you can set. Those kind of things as an input, as you will typically you will evaluate from the output the filling status and the filling time, how long will it take, and the porosity level you can check, and the infusion time you can check, and the pressure applied to the mold so you can check, and the temperature you can check. Okay, this is instantly you can get this kind of output if you set input like this. So trial and error. You on computer, you can optimize your parameters. You can refine your input parameters. Then, if you have satisfactory, you have satisfied the output here, then that chosen parameter set will be tried on your real molding process. Then, presumably, maybe your optimal, real practical optimal parameter set will around that. Maybe 2 or 3 times test run will make your final manufacturing setup as a virtual optimal process, right? So this kind of specialized purpose program will give you great freedom to choose manufacturing parameters. So the prediction of fiber orientation, residual stress, defect identification, all of those can be possible from. Okay. And future trend in composite modeling is multi-physics integration will be improved. Artificial intelligence will be engaged. In that case, maybe you don't need to put your input algorithm by yourself, input parameters by yourself. It will be chosen by AI. If you want to have something, then you can just describe what kind of output you want to have, what kind of facility you have. If you let the program know, then automatically it will find the first optimal trial set that is possible after AI is embedded with the special purpose programs. Okay? This is what is benefit if you use specialized software or even general purpose software can be used. In the case of what kind of benefit you can enjoy, I just try to introduce you. Okay? Education? No. So 2 lecture time is already. Yeah.
Which simulation is more important, like process modeling or structural modeling? Which one is more important for the component?
For the composite materials.
Which kind of simulation is very
processing.
important, or structural modeling?
I think process modeling is very good. Okay. And the product modeling is before manufacturing process. So in design level, maybe you have no idea about product itself. Maybe it is given to you. This kind of product I wanted to have. So just manufacture this for me, something like that. In that case, you don't need to run the structural analysis, something like that. But if you want to design product by yourself, in that case, before starting the processing simulation, you need to define the product, right? In that case, structural analysis should be used. Yeah?
So like means if I am to produce any product, firstly we should go towards the product modeling, and after product modeling, if I have finalized the product, this material will be used, then come to process simulation.
Correct.
Thank you.
Okay, thank you so much. Today, this is my two lectures. Okay, so I'll see you tomorrow. Thank you very much. Thank you. Oh, it's cold.
Okay, so shall we start? So let me introduce myself first, okay, because so I am Dr. Narendra Kumar and I am working here as an assistant professor since 2019, and my research area basically is 3D printing, or you might be known as this technology as additive manufacturing, right? And I am doing various projects with ISRO and SERB, and recently I have received 2 projects from BIS only, right? So today I will be talking about the additive manufacturing of composites. So here, because I have chosen this topic for this lecture particularly, because the theme of this workshop is modern composite material, right, and manufacturing. So nowadays additive manufacturing is becoming very popular for composite manufacturing, right? Because I think in the previous lecture professor has discussed about the different manufacturing techniques, where he has already covered the filament binding and other techniques, but he has not covered about the additive manufacturing. So I will try to give you brief idea how can you use this particular technology for composite preparations, and if you choose this technology, what are the advantages, right? What kind of failures you may face during the preparation, and what kind of challenges may be there, and how can you overcome with those challenges. Okay, so I will try to cover those aspects. So this is my brief outline. So initially I will be giving the idea of additive manufacturing, and then I will be talking about the composites in additive manufacturing and types of additive manufacturing. Then finally I will move to the polymer composite developments using different additive manufacturing processes. So my lecture would be more focused on the polymer composites only, because here I have only 1 hour, right? So if I cover polymer matrix based composite, ceramic matrix based composite, then it needs a lot of time. So I will try to cover all the aspects related to the polymer composites through additive manufacturing, right? So if you find any difficulty or any if you have any query, then you can ask after my lecture, right? Okay, so let me ask one question first. What is additive manufacturing? Do you have any idea? Because I can see here Bisal is doing PhD in additive manufacturing, so he has idea about this. But anyone other than the Bisal and his friend, anyone? What is additive manufacturing? Have you ever heard about this technology? No? 3D printing? I think all of you, because nowadays it is very popular, and I think all the institutes nowadays have this particular technology in their labs, right? So additive manufacturing, sir, you can change your seat, otherwise it will block the view. So it is a process of making the objects, 3D objects, but in layer by layer manner. We add material at a time, only single layer deposited, then we add material, another layer of the material, then another layer of the material, and we add the layers until the whole part fabrication is achieved or completed, right? Now the question is how it is different from the conventional manufacturing like subtractive manufacturing. If I talk about the conventional manufacturings, I think most of the techniques are based on the subtractive manufacturing. If you take the example of injection molding, for mold making we need to use machining, we need to use milling process, right? So milling means we need to remove material from the large stock, right, to get the desired shape. But here the idea is different. In this slide you can see that initially we take material either in the powder form or in the filament form or in the liquid form, right, and then we feed that material in the machine, and then finally we achieve this 3D object, right? However, if I talk about the conventional manufacturing, here we take large size of material or the stock, and then we remove material in the form of chips, right? So these are the chips, this is the waste material, and this is the desired geometry that we have achieved through this machining, conventional machining process, right. So there is a difference. If you compare these two, you will find the difference in the waste, right. Another difference that I will share, I will discuss in the next slides. Okay, so this is a basic difference that you can just have idea. Okay, so what is the history of additive manufacturing? So it was started late means in 1980s. So the first process was stereolithography, right? Stereolithography, that was the first 3D printing or the additive manufacturing process. And then selective layer sintering was also started that time. And in 90s, filament deposition modeling or fused deposition modeling process came into the existence. Okay, so this was developed by Stratasys company. Stratasys basically was the inventor, okay, or that company who invented this particular technology, and this technology was filament based technology where we can use any kind of thermoplastic in the filament form. So, and then after 2007, when the patent was expired, okay, all patents related to the 3D printing were expired. That time, many companies launched their printers on the same technologies, right? Whether it is FDM, whether it is SLS, whether it is SLA. Nowadays, one printer DLP is very popular. If you, I don't know whether you know about that or not. Along with FDM, okay, DLP is also becoming popular, and you can get this SLA. Basically, DLP is nothing but the similar to SLA, is lithography, right? So DLP you can get only for 20,000 rupees. FDM you can get only for 15,000 rupees, 18,000 rupees, right? So DLP is becoming popular because of its cost, because it's equivalent to the FDM process. Suppose you want to purchase new machines, or you don't have money, you have only 50,000 rupees, you can purchase both the machines. You can purchase FDM as well as DLP. DLP is digital light processing. It is very similar to the SLA. SLA I will discuss, right? Then other companies entered. Then nowadays you can see this 3D printing now a $1 billion industry. $1 billion industry nowadays. People are having a startup based on services. They are providing services. You just go there and you supply your STL file. They will print for you, right? You just discuss your idea or your problem with the industries. They will solve through 3D printing, right? So this is the history. Now this technology is basically it's in the matured stage. More materials have entered, right? Or new machines are coming. They have more speed features, because earlier speed was the issue. Suppose I want to make a small cube, it will take around 2 hours. But now new machines are there, they will take only 15 minutes. They have changed hardware completely. I have also released one PO for new machine that has very good speed and very good features. Those were not available in my previous machines. So it means new manufacturers, new companies are focusing on this technology, and they are coming up with new 3D printers with some novel features. Even some of them have incorporated AI camera. So camera will capture the the current movements. If any problem there, printer will be stopped automatically. So those features actually nowadays are available with printers, right? Now why we are talking about the additive manufacturing of composites? What is the reason? So here I have mentioned few reasons like customization, and second one is the rapid prototyping and iterative design, and third is very most important, that is the complex geometries and design. Complex geometry or customization, because 3D printing or additive manufacturing offers the the printing or the manufacturing of the objects with customization, because here there is no requirement of tool, right? No requirement of mold, right? So just what we need only CAD model. If you have CAD model, if you have STL file, you can directly feed that file into 3D printing machine, and 3D printing machine will read your file, the program which you have loaded, and it will start automatically depositing material. So complexity is not a big deal nowadays, but this complexity is very difficult to achieve through conventional manufacturing. For example, if I want to make a complex object, right, through injection molding machine or the compressor molding machine, in that case what I need to do? I need to make the mold first. So for that complex object, mold making itself is a challenging task, very challenging, because we need to write the program, right? We need to design the fixture, we need to think about the tools that will be used to make that complex mold, and it will take a lot of time, right? And lot of energy will be involved there if you go through the conventional manufacturing. But when you opt additive manufacturing, it provides the flexibility. You can make your own part with customized features. Second thing, complexity. So complexity is not an issue nowadays. I'm not claiming that any complexity can be achieved. No, this is also not true. If you say, sir, can we make this? We have to assess the features of the 3D printing machine that is available with you. Then only we can say this complexity can be achieved with the available machine. Otherwise, we cannot claim any complexity can be achieved by FDM, or this complexity can be achieved by SLS printer or SLA printer. So whenever you are planning to make a complex object, first of all you need to check the machine, what machine you have with you, right? What machine do you have, and you assess all the features, specifications of the machine. Then only you just go for the geometry development or the CAD model development. Otherwise, what will happen? Suppose you have given one feature in your CAD model, right? And when you convert your model into STL file, right, then you will feed that STL file into the software. That software will generate the program. But when you load that program on the machine, that feature may be missing or may be missed by the machine. That will not be available in the final part or final printed part. Why? Because of that machine is not having that much capability. That fine feature may be missed by the machine. So whenever you are going to use any additive manufacturing system for the printing, in that case first you need to check the machine parameters, right? What is the minimum size that can be achieved with the machine, right? What are the other parameters? Accordingly you should go for the CAD modeling. Otherwise consequences may be different, right? So this is the this slide highlights the importance of additive manufacturing in modern manufacturing. Okay, and here we can reduce some material waste that I have already shown you, and this thing is also very important. Simplified supply chains. How? Simplified supply chains. Ajay, do you know about the NASA refabricator? NASA refabricator. Have you ever heard about this term, NASA refabricator? Acha, how many of you know about International Space Station? International Space Station. I think everybody knows. Suppose they want a nut and bolt, right? They want nut and bolt to assemble two components. What they will do? They will order to NASA, then NASA will arrange rocket and they will send that nut and bolt to ISS. This is as per the conventional supply chain, right? If suppose if I talk about the conventional supply chain, what I will do? I will talk to NASA scientists, right? Then I will tell about my requirement. I need nut and bolt to assemble these two components. Now what NASA will do? NASA will arrange a rocket, right? And they will load those components on the rocket, and then rocket will go to the ISS. So what is the cost? It is too much, right? We cannot imagine. But what NASA has done actually, they made a printer. The printer name is NASA Refabricator. Okay, so they have sent that printer on the ISS, or they deployed that printer on the ISS. So now what they do, if they want any small item, right, or anything for assembly or for some other purpose, they print those components or those parts there itself. So that's why I am saying simplified supply chain. So this thing will be replicated here also, because now we are moving toward the industry 4.0. Okay, so small or localized 3D printing centers will be established across the country, similar to EV, because EV nowadays electrical vehicles are getting popularity. Now what will happen in the future? Similar to the petrol means filling stations, we will have the charging stations, right? So in the industry 4.0, in the coming future, in the coming 10 or 20 years, we will have the 3D printing hubs. In Jalandhar there will be one 3D printing hub. In Panipat we will have one 3D printing hub. In Chandigarh we will have one 3D printing hub, right? So this will disrupt the existing supply chain of the materials because of the capabilities. Because when you will have the facility, obviously you will demand for the customized products, right? So now no need to go to visit the shops. You will directly go to the 3D printing hubs. Okay, they will make the shoes for you. They will make the customized items for you, right? So it will simplify the chain. So that's why it's very important to understand about additive manufacturing and the additive manufacturing of composites through, okay, because this is important topic, because I have got funding based on the composites only. Because when I was writing proposal, right, when I was planning to submit a proposal, I thought what should I do, on what topic I can write a proposal. So one proposal that was clear, because ISRO has mentioned the topic, you have to submit only on this topic, right? But when I was submitting a project to DST SERV, that time I just prepared my proposal on the high performance polymer composites, and surprisingly I got funding of 55 lakh rupees. So why government actually investing money on this area? Because this is important, right? If you write a proposal on handley technique, you will not receive funding, because that is conventional one. So if you come up with new idea or new manufacturing technique, obviously you will get funding also, you will get PhD also, you will get MTech, you will get everything. Okay, so this is the importance of additive manufacturing in the modern manufacturing era. And here I have highlighted the advantages of additive manufacturing for composite parts. So it provides flexibility in the design. Vivek, can you give me that box? Okay, here. Sorry. What is the, yeah, like this is the honeycomb structure, right? This one. So I can make any structure, I can design my own part, right? So that's why first one is the design flexibility. So I can design my part. Long back actually, today I found these parts in my office, so I thought I should show you. During my PhD, what I did, I made lot of things. So this is customized keychain, and on the center, if you look at the center, right, in Hindi I have written Narendra. Okay, and my lab name actually has been printed in the center, and on the outer periphery I have written my college name. So design flexibility, right? First advantage is the design flexibility. I can design my own part. It gives flexibility to the user. They can come up with new ideas, new designs. So this is one of the advantages. Second is the lightweight design. So lightweight means this is lightweight. I can plan how I will put lightweight feature in the components. So I can use honeycomb structure. I can use any other pattern also. So lightweight feature is there. Okay. Otherwise, what we do when we make composite, we try to find the lightweight reinforcement filler material, right? We look forward toward that direction, na? But here, material wise, you can make it lightweight, and also design wise, based on the design, you can make the parts lighter. There are two things, and this reduce lead time. Is it true? Can we reduce lead time? How? Yes, because tooling is not there, right? Tooling requirements are not there. We are not making any mold. Otherwise, in the conventional manufacturing, what we do? First we make mold. So it takes time, 2 days, 3 days, 4 days. But in 3D printing, no tooling is required, no mold is required. So obviously, it will reduce the lead time. And fourth one is the on-demand production. No need to store inventory. Suppose today I got the offer. Suppose today I get the order from the industry. Okay, please make this part for us. What I will do? I will just prepare STL file and then directly feed that STL file into 3D printer, and 3D printer will develop the part for me, and then immediately I will supply that part to the industry. So no need to maintain the inventory. So this is one of the feature or advantage with EM. So mechanical properties of AM composite parts: we can increase strength, we can also reduce the weight, as I already discussed with you, right? Okay, what kind of applications we can target through additive manufacturing? Here I mentioned especially 4 industries. First one is the aerospace industry, second one is automotive industry, and third one is medical devices, and final one is the energy sector. Energy sector. So in the aerospace, what we can do? We can create or we can develop strong and lightweight components, right? Strong and lightweight components. So this, with 3D printing we can achieve this. We can achieve this, or we can use the 3D printed components in aerospace industry, because as I told you, 3D printing provides, or additive manufacturing provides, the design flexibility. So by design also you can provide you can reduce the weight, okay, and by just making some new composite you can reduce the weight of the overall weight of the component, right? Then automotive, similarly engine components, suspension parts, body panels, here also similar kind of requirements, okay, as we had in the case of aerospace. So here also we can improve the fuel efficiency. And third is medical device. I think this is one of the sector which has been benefited with this technology most. Medical industry. How? One of my friend who is based in Nagpur, what he does? He supply temporal bones, models of temporal bone, compliance, not implants basically. temporal bones for surgical simulation. What is surgical simulation? Before surgery, doctor want training, okay, or we need to give training to the doctor. So this 3D printed components or this 3D printed bone can be used for that purpose also. Implant is also one of the application, but this area has huge potential. You can use the components for surgical simulation. You can use the components for as a implant also, right? Case to case basis, the application of 3D printed parts may vary, but he is getting he is earning money by using 3D printing, right? And he is doing very good in this area. And what he has developed composite also, because earlier what was happening, he was using ABS only to develop the temporal bone. So when doctor was taking training on the ABS material, right? So that time haptic feedback was different. Force, every parameter was different. So when they were, for example, suppose they wanted to do drilling on the temporal bone, on actual bone, that time the feedback will be different because there is a difference between the material. Because bone is having different properties, right? And ABS has different property. So that is why what he did, he developed a new material, right, by doing R&D, and he come up with new material that has the bone-like properties. Now again the same thing they are doing. Again they are giving training to the doctors. Now they have more or less equivalent kind of feedback when they are drilling or they are doing something with those bones. So accuracy of the doctors will be increased. So in this way also we can train the doctors. Next is energy. So energy means wind turbine blades. The design is very important parameter, right? So you can design the blades, you can increase airflow or you can increase output. So those things can be done. And this heat exchanger is one of the area. I think most of the people are exploring this area with the additive manufacturing. One of my PhD has also done research in this area where we have made the polymer based heat exchangers, and we published articles on this particular topic, right? So what are the different materials that can be used in the AM composite printing? So reinforcement materials like carbon fibers, glass fibers and other fibers can also be used. Another matrix material, we can use the polymeric materials like EBS, PLA, PEEK and epoxy resins can be used also, right? Properties that are relevant to the additive manufacturing. So here the mechanical properties like high strength to weight ratio, flexibility in the load bearing. Flexibility in the load bearing means we can align the fiber, we can orient the fibers along the load direction, right? We can change this because we have the nozzle or the mechanism by which we can control the orientation of the fiber. Like in the case of continuous fiber 3D printing, I will tell you later on. So flexibility in load bearing, impact resistance, thermal resistance, in which we can just increase the heat resistance, right? So that your composite will withstand at high temperatures, and thermal insulation, electrical properties. So conductivity, I think you can work on conductive materials. You can increase conductivity by adding some fillers like graphene and CNT, insulation. So these are some of the properties that are generally increased, or you can say the most of the materials are developed to increase these properties, okay, case to case basis. Some of them may focus on the durability of the composites. One of my PhD scholar actually is working in this area where we are trying to increase the durability because if you know about 3D printing, you know PLA is most popular material, right? PLA, but still its durability is unknown. Suppose I make a component using PLA, but what is its durability, for how much time I can use it, that is still unknown. 2 year, 3 year, 2 year, or 5 year, or 10 year. So what we are doing, we are exposing the PLA components in different environment, right? And then we are checking their performance under UV, under salt spray, right? So lot of conditions we are virtually creating through the apparatus, and then we are checking their performance. So this is also one of the area or property. Customized property, nowadays graded properties also there, gradual variation you can achieve. This is I think one of the most hot topic, or you can say this is one of the area that can be achieved, or that can be done through 3D printing only. Gradual variation, layer by layer variation we can provide, okay, through 3D printing only. By using injection molding, by using any other process, you cannot do it, but with 3D printing this is possible. Gradual variation in the composition can be achieved. So this is I think one of the area that is very popular now. Functionally graded structures, right? FGS or FGM, a material. So this is I think very new area where people are working. So common composite materials in AM, so carbon fiber reinforced polymers, carbon fiber reinforced glass fiber are there, nano composites, some hybrid composites are also there in this field. And this is the emerging area where you can develop some bio based composites. Smart composites means smart composite with embedded sensors. So this we have printed in our lab, this one, right? So this is epoxy, and we have 3 layers in this, and lower layer and upper layer we have used epoxy, but inside between the epoxy layers we have also deposited copper material, right? This is also one of the area. If you go through conventional method, so through conventional method you have to go for etching, right? Lot of processes or steps are involved, but with 3D printing we can easily achieve. So this is also one of the area that you can explore. And so now here I have categorized the additive manufacturing based on the material type or the matrix type. So in the first category I have mentioned polymer matrix based additive manufacturing. Second is the ceramic based, and third is the metal based, right? So 3 categories we have taken here. So in the polymer, where we can make polymer matrix based composite, so here we have FDM, we have SLA, we have SLS, we have direct ink writing, and in the second category we have winder jetting. This direct ink writing can be used here also and here also, right? And this process also can be used here, okay? And then metal based, powder bed fusion, direct energy deposition. So I am not going to cover in the detail this technology. So what is FDM for composites? So those people who do not have any idea about FDM, so let me cover the working principle of this technology first, then we will move to the other slides. So here if you look at this schematic diagram, here what we have this build platform, right? And we have the this build platform, we have 2 spools, right? And here we have this extrusion head. So we are supplying material in the filament form and it is going toward the extrusion head, and here we have heating mechanism, right. So due to this heating mechanism, the temperature of the material is increased up to 200 degree centigrade or 220 degree centigrade, then it is deposited on this plate form, right. So initially we deposit material and form first layer, then second layer, third layer, fourth layer, right, up to 1000 or up to 2000 layers, okay, depending on the height of the specimen, okay. So this is the principle. Now suppose I want to make a composite material for this particular process, what steps I need to follow? So first is the, initially I will select my matrix material, it may be PLA, it may be ABS, it may be nylon, it may be PETG, right, and then I will select my reinforced material also, right. Then in order to mix both the materials, matrix material and the reinforcement, what I will do, I can go for melt mixing directly, or else I can go for the solution based mixing, solvent based mixing. Melt mixing means here I can use twin screw extruder. I will directly feed my reinforcement and the matrix material into the hopper, and then I will just rotate the screw, and where we have the heating arrangement similar to the FDM, and then material will be mixed through the melting only. But in the solution based mixing, what we do, initially we take the solvent, right, and that is selected based on the selected matrix material. Suppose matrix material is ABS, for example. So acetone is the solvent of the ABS. So I will take ABS and acetone both, and then I will use magnet stirrer, or I can go for the ultrasonic stirrer also. So I will mix, I will prepare the solution, then after I will add the reinforcement material, then again I will mix it. So after means ensuring the mixing, I will dry the composite, okay, and I will just pour the material on the flat sheet, and then I can keep it in the furnace. So solvent will be evaporated, and after that, after ensuring the dryness, I will cut the material into the small pieces, or I can convert them into the small pellets pieces. Then I will feed it into the filament maker, okay. So filament maker, when we feed that material in the filament maker, that will give us the filament. But filament, see here I have mentioned the size of the filament. 1 point, we have to ensure the diameter 1.75 mm, okay, plus minus some tolerance may be given, but usually we try to make, or we try to achieve this diameter in the filaments. Then only we will be able to feed the filament into 3D printers, right. Now, so printing considerations, when you are planning to make a composite for FDM, then yes. Printing consideration means here we need to ensure the printer nozzle is suitable for the composite that is under consideration or not. Why? Because suppose you are just going to add the hard material, okay, that hardness is greater than the nozzle material. In that case, what will happen? It will wear out, the nozzle will wear out, right. The size of the nozzle will be changed. So you need to check this first, okay. So in that case, you can use good material nozzles, stainless steel nozzle or other materials are also available. So you can check the compatibility of nozzle with that composite, and then you need to optimize the settings, printering settings like parameter, temperature, bed temperature, okay, speed, that you have to be you need to optimize them, otherwise what will happen, you will not be able to achieve the proper flow rate, proper adhesion. For example, I have added something in the PLA, right? Usually I print PLA at 200 degree centigrade, but when I add some filler material, add some reinforcement, it will change the property, because we have ensured the proper dispersion of reinforcement into the PLA matrix. So in that case, I have to either decrease the temperature or increase the temperature, because in one of my case recently, because my scholar he is trying to develop a filament of PLA and ZNO, right? So when we are mixing it with ZNO, we are not able to convert that composite into filament form. It is increasing the flow of PLA, and I have consulted about this with the CPAT Bhubaneswar. Even they are not able to make the filament. So sometimes these issues actually might be there. So be ready for these kind of challenges. Now we are finding different way how to tackle that issue. So that is why suddenly means the property of the matrix may be changed, okay, due to the addition of the reinforcement. So this is, I think, the very important thing that you need to consider. And drying is also very important, because composite filaments sometimes may absorb the moisture. So ensure or dry them before printing to prevent any defect. And sometimes you need to do the post processing, surface finishing, right? Thermal treatment sometimes it may be required. So I'm not going to cover in detail because of the time. Oh, quickly I will finish because of the time. Okay, so key challenges: dispersion of the reinforcement is very important parameter. So poor dispersion can lead to the weak spot or the defects within the developed composite, right? It may create the holes, right? It may reduce the strength of the material, flexibility, elongation at break, the value may be decreased. So you need to mix the reinforcement and matrix properly by using some good mixing mechanisms. So ultrasonic mixture can be used for this purpose. Nozzle wear, you need to take care about this because we have already discussed. Printability, you need to adjust the parameters, okay, thickness, height, support, to avoid the clogging or to achieve the desired mechanical properties. Okay, next process is the SLA for composites. SLA for composites. So SLA is stereolithography. It is liquid based process. Resin, here we use the special resin that is cured under UV light. No heating mechanism is involved in this case. Here just we use a material. When we expose that material under UV light, it is solidified. Okay. So here this is under this also, because the material form is resin. So you can take the resin first, then you can take the reinforcement material, then you need to do mixing, right? And then after sometimes you need to add some photoinitial adjustment because it may affect the curable feature of the material, right? Suppose before mixing the curing time was less, for example, but after mixing the reinforcement in the resin, curing time may be increased or decreased depending on the material that you mix in the resin. So you need to adjust this particular value So you can add photo initiator to ensure the proper solidification. Light penetration, because it is, as I told you, no heating mechanism is involved in this particular process. So here we are dealing with UV light, right? So here I mentioned one point, reinforcements like opaque particles, they can block the UV light. So if they block UV light, what will happen? That portion will remain in the liquid form. So obviously the desired geometry will not be misprinted, right? So this is one of the problem. So okay, I will provide these slides so you can go through them. Yes, one key challenge is there, that is the sedimentation. Due to gravity, because here we use a tank, and when suppose you have prepared the composite by just taking the resin and the reinforcement, but after a certain period of time, right, what will happen? The reinforcement fillers may be settled down on the base. So on the upper portion you will have the the different dispersion, and on the at the bottom high dense dispersion of the these filler particles may be available. Okay. So it will change the properties. Is that clear? So sedimentation is one of the key problem or key challenge when you go for the composite development through SLA, right? Second is light scattering. Light scattering, right? So here what we can do, we can reduce the particle size, or we can use the transparent reinforcement to minimize the UV scattering. Another process that is also the liquid based process. So this is direct ink writing, right? So this process we have also developed in our lab, and the part that I have shown to you, that copper and the epoxy printed component, that we have made through this technique only, direct ink writing. So direct ink writing means here we prepare ink or resin, we prepare the resin in the ink form, then with the help of syringe we just deposit the material on the plate form. So here two mechanisms generally are used. One is the heating mechanism, thermal based curing systems, sometimes that may be used, and second is the UV curing based mechanism. We can use UV light, okay, on from the top we can just throw UV light on the material which is coming out from the nozzle, okay, in order to solidify that, or in order to ensure the solidification. So here similarly we have the matrix based ink, so any ink material that you can choose, and other matrices like conductive polymers, or you can use conductive material like copper, aluminum ink, and other inks which are available in the market. So be flown on the surface, right? It will be spreaded immediately after coming out from the nozzle, right? So that is why it is very important to control its rheology. So you can control it by using the plasticizer, thickener, so they are available. Viscosity, stability, right? Loading the ink nozzle, this is the these are the steps. So post processing sometimes required, further curing is required. We can keep the samples in the UV furnace, okay, and then cleaning, surface finishing. So key challenges is rheological balance. When you when you are adding reinforcement particle in the resin, so balance in the rheology is very important. And sedimentation, again the same problem that was available with SLA, okay. Nozzle clogging, because here we are depositing material from the nozzle and nozzle diameter is very small. So in our case, what is the size of nozzle, Vivek? 0.1 mm? 0.1 mm. So 0.1 mm is very small. Suppose the filler particles are agglomerated, right, inside the resin. So their gross size may be increased, right. So they will block the or they will clog the nozzle. So this is one of the issue. And then SLS, selective laser sintering. Here what we do, we use material in the powder form. So powder means from the top we just use the laser source, right. So laser beam actually moves along x and y direction, right. Then sintering takes place, okay. And then platform is lowered down by the layer thickness, okay, equal to the layer thickness, and then again further powder particles are added with the help of recoater arm, and then again that same process is repeated until the whole part fabrication is completed. So here we use material in the powder form, so we can select polyamide, polyether ketone. I think PEEK nowadays PEEK is very hot topic, PEEK material, because it has capability to sustain at 400 degree centigrade, 300 to 400 degree centigrade, right, and it has lot of application in biomedical engineering. So people are processing this material in the pellet form also, in the powder form also, right, and in the filament form. I think very few printers are available in the market, right, those can handle this PEEK material. Otherwise ordinary printer cannot print this PEEK material, polyether ketone. So if you are planning to do some research, you can select the matrix of PEEK matrix. It will give you new dimension, okay. It will give you the idea, means you can publish lot of paper by taking this PEEK material, okay. So here mixing and blending technique can be used to just prepare the composite, right. So sometimes you can coat the powder particles, you can use all the melt blending also, right. Again you can convert this granulate that you can granulate, again you can convert them into the powder form. So then particle size, flowability, thermal behavior optimization can be done. So key challenges are homogeneity, achieving even dispersion of the reinforcement in the powder matrix, right, powder flowability, laser energy absorption. So these are the challenges, okay, that may occur during the composite development through the SLS. So I am going to skip this. Let me tell you these, yes, challenges and limitations of AM composites. So first challenge is scale up, because with injection molding machine we can produce component at mass level, but with this the process too slow. Initially you have to prepare the composite, then slowly it will make the component, right, by adding material in the layer form. So scale up is one of the issue. Second is material development, because we have seen when we are changing the process we have to change the way also. For powder based AM processes we need to use different process for composite preparation. For FDM we are using different process for composite preparation, right. So material development is bit difficult, right, and it has limitation also. Then cost. So AM composites can still be more expensive than traditional composites. If I make any component by using the additive manufacturing, right, obviously it will be costly, because I will do reinforcement, I will fine tune the parameters. So it is a bit difficult, right. So I think these are the challenges and limitation in this area. And what are the future trends and innovations? Multi-material printing. multi-material, because currently with if I talk about FDM, mostly dual nozzle printers are available. Dual nozzle, only we have two nozzles. Two material can be used at a means to make a part, right? Suppose I want to make a print the base material by using PLA, I can do it. Upper portion I want to use for upper portion I want to use ABS material, I can use the ABS. But nowadays what is happening? One company, that is Bamboo Lab, right? Bamboo Lab, what they are doing? They are selling their printer with this multi-printing feature. Multi-printing means only 4 materials. You cannot use material more than 4. 4 materials only can be used, right, to make a single part. So they are calling that printer is multi-material. But still, if you want to use means more materials to make your part, again it is very difficult. FDM, similarly DIW, we have to increase the number of nozzle, it will increase the complexity. Similarly for SLS, because we have one platform where we are recoating powder and powder again and again. So how I will change the powder material for each layer? So processing of powder is very difficult, right? Because if I change the powder particle after 1 layer or 2 layer, 3 layer, so with SLS multi-color printing or multi-material printing is not possible. Or if you modify the existing SLS, it will be very complex or it may take a lot of time, right? So this is, I think, one of the area, multi-material printing. This can be the game changer, okay, in near future. If anybody comes with the new idea with multi-material printing, then I think this will get the market, okay. Automated design optimization. So in the coming time, AI and machine learning will be used to optimize the designs, right? जैसे मैंने आपको because I have shown you one part, right? That honeycomb one. Where is it? Yeah, this one. This one. So here I have just used this honeycomb pattern for whole. I have applied this honeycomb pattern for this whole part, right? But if we apply EI based some mechanism, okay, so that will optimize the design. Where I need more strength, it will change the pattern. Where I need only less strength, it will change the pattern automatically. I need to give the shape only. I will feed the shape only. It will give me the optimized design of the component. Similarly, okay, increased production speed. Still speed is slow, because as I told you, if you make a small part, right, this much small, what will happen? It will take around 30 minutes or 1 hour, right? But with injection molding, machine will take only 1 second or 2 seconds. Okay, so this is still, I think, this is still one of the challenge, or this is one of the area where you can work on the production speed. You can try to increase the speed of the 3D printing systems by adding new motors, new mechanisms, new hardware, right? So this is all about the AM of composites, right? If you have any query, any suggestion, you are most welcome to ask. Any question, any query if you have related to topic. Yeah, in case of FDM, sir, short fiber, in case of short fiber, it cannot be achieved, right? We cannot control the orientation. Yeah, option, we have options. I think IIT Mandi has one printer. In that, by using that printer, you can feed continuous fiber along with the thermoplastic. And we are also developing, sir, in our lab. I think we have conducted few experiments where we achieved the continuous fiber reinforcement and epoxy. This is epoxy, and if you look at this part, you will see the continuous fiber that we have embedded inside this. दिखा देना Prof sir, पीछे दिखा देना. Okay, so thank you. Any question? Okay, thank you very much. Thank you, thank you. Sure, I will have, today I am busy, but tomorrow we have, some tutorials. So in that tutorial we will try to show you the setups and the capabilities. Okay. So today after lunch at 2:30, you just please assemble here, and Sudhanshu will guide you. Okay, he will guide you for the next tutorial. So we will go in the textile technology department, where they have some setups, and they have done a very good job in this area, right? So they will discuss their work, and okay, Sudhanshu, please consider them. Okay, thank you.
Right, we will start once again from the start. So I am Dr. Zanzarrao Kamble. So today we will be discussing about the real life problems of the composite materials, and we'll try to understand what are these real life problems in the related to composite materials, and how to solve these particular problems. So we know that composite materials are nothing but a combination of matrix and the reinforcement, and its mechanical properties are superior compared to any one of these, right, either matrix or reinforcement. So majority of you might be aware that maybe aware of this laminated composite, right? So multiple layers of fabrics stacked together and impregnated with the resin material, right, and cured using let's say for example at the room temperature, or maybe at certain temperature using the compression molding technique or vacuum bagging technique, right? You must be aware about this various composite manufacturing techniques, right? So let me show you some this fabric preforms. I have specifically prepared this for this particular session. So this is the glass fabric, right? And we can produce the glass laminate, that is laminated composites. So for example, we can stack the fabrics one above the or other, right? And we can have multiple number of layers depending upon the required thickness, right? So for example, let's say the one layer thickness is, let's say 0.1 mm or 0.2 mm. Generally it is 0.1 mm. So depending upon the required thickness, for 600 tex yarn you will get 0.1 mm thickness, right? Thicker the yarn, the fabric will be thicker, right? Or you can arrange these particular layers at certain angle also, right? For example, let's say this is the 0-0 arrangement. For example, this is 0-90 arrangement. So you can have some layers at 45 degree or some other angle, maybe depending upon the properties required. So you must be aware that this composite is designed. For example, this laminated composite. So this is the carbon fabric. This is the 12K carbon yarn fabric. And here also you can produce laminates based on your requirement, right? According to the, you can arrange these layers at different angle based on the properties required in that particular direction. Because एक चीज यहाँ पर important है that textile materials are anisotropic in nature. You know that, right? You have some properties in 0 and 90 degree, and at bias angle you will be having different properties. So ये anisotropic है, and our composite material, that is textile reinforced composite material, is also anisotropic. So we will start with the what is the main problem during in the composite material. One of the major problem is the voids. You may be aware about the voids.
Porosity.
Yes, void means air gap. Right. So it is ideally in the composite material we know that matrix is the continuous phase, right, and reinforcement is the discontinuous phase. So when we are producing, let's say this is the one of the composite material. Let's say this is the composite material we have produced. So in this composite material, the matrix should be continuous inside this particular composite structure. But actually it doesn't happen. Ideally it should be continuous, but actually because of the limitations associated with our techniques. For example, we are using, let's say, hand layup technique. In hand layup technique, what we do, we simply take the reinforcement, right? For example, अगर ये plain woven कपड़ा है या कोई भी, this is the twill woven carbon fabric. So what we do, simply let's say 4 layer का कपड़ा अपने को, for example, we have to make a composite with 4 layers. So what we are doing is, we are taking one layer, applying a resin, epoxy resin for example by hand, then putting a second layer on it, again applying the epoxy resin, third layer, fourth layer, like that. And we are applying some dead weight on it. Suppose you are curing at room temperature, then we simply keep it like this only for maybe around 24 hours. Generally, epoxy resin is cured at 24 hours.
तो epoxy resin might be inflammable ना, जल जाता होगा?
नहीं,
epoxy जलते नहीं.
Epoxy resin is not flammable. Okay. So you can cure it at higher temperature also. मतलब for example at 120 degrees for around 20 minutes. Epoxy resins comes in various grades depending upon the composite manufacturing technology. For example, if you are manufacturing, let's say, and also depends upon the type of application. For example, the aerospace grade epoxy resins are different. For example, you have some automotive composites. For automotive application, the epoxy resin grades will be different. For some other applications, it will be different. And depending upon the technology also. For example, you are producing filament wound composite materials. In that case, the epoxy resin grade will be different, where the pot life is higher. You know pot life of the resin, pata hai aapko? So let me tell you what is pot life. So we will have one more session on the development of composite material, hands-on experience. So in that also we will discuss it in detail. Pot life means what? When we are mixing resin and hardener together in a desired proportion, for how long this particular resin is the curing is not started. Resin is in the you can say it is in a flow. It is in a flow, and you can apply it without any problem. So that particular time, at how much time any resin hardener reaction starts. So that particular time we call it as a pot life. And in case of filament binding, suppose you know filament binding process. Pata hai aapko filament binding? Yes. So in the filament binding, you know the binding of the filament it takes long time, and therefore in that case the resin required is different grade. So it has a higher, longer pot life. So in case of compression molding, we use resin which is having shorter pot life, maybe 20 minutes, 30 minutes, maybe maximum 1 hour, right? For example, vacuum bagging, again you can have a resin with longer pot life when you are having a larger component. For example, windmill blade you are manufacturing. So it's a longer part, for example around 40 feet, 35 feet longer part. So in that case again you should have a longer pot life. But small parts you can have a resin with short pot life. So what happens is that because of this, if you look at the different composite manufacturing techniques, let's say it is a hand layup or it is a compression molding technique, where you are curing at elevated temperature, so that your curing time is reduced and you can produce multiple components within small time. Or let's say vacuum bagging technique. So you see that since the technique is different, what happens is that the properties of composites are also different, right? And one of the reason is the voids. One of the reason is the void. Void is nothing but a air gap in the composite material, right? And that air gap actually causes stress concentration. When that particular composite material, let's say this is the composite material having voids in this particular composite material, let's say. So what will happen under the loading, let's say any type of load, tensile load or bending load or impact type of load, because of that void, that particular area becomes an area of stress concentration, and from where actually your failure start. For example, this is the one sandwich composite material, and let's say this is the sandwich and you are using it in the flooring. So you must be aware that in the floorings of, for example, aeroplane, for example, your superstructure of ships, right? So where in the flooring we use honeycomb type of composite materials, right? Because they are high energy absorbing composite materials. And let's say if there is a void in these particular structures at any place, so what will happen? From there actually your failure start first. that particular point becomes a stress concentration point. And why it becomes a stress concentration point? For this, you must be aware of, or you must be knowing the composite failure mechanism, right? आप सभी को पता है composite failure mechanism. So what happens is that whenever load is applied on the composite material, that load may be tensile, compressive load or bending load. Matrix material, the continuous phase first takes the load, and it is distributed right throughout the structure, and it is transferred to the reinforcement. And how much strong your matrix and reinforcement interface, that decides how efficiently your matrix will transfer the load to the reinforcement. And if there is any void, so void is again a defect, so that particular void will become a stress concentration point, and from where your composite will start fail or deform, right? So this is the one of the common problem in the composite material, that is void, and how to avoid these particular voids. So one of the way is to use vacuum bagging technique, right? So vacuum bagging, आप लोगों को पता है vacuum bagging technique और vacuum assisted resin infusion technique? आज ही पढ़ा है, okay. So we have actually ordered that particular setup, so that's why we are currently not having. Maybe in the next week we will be having this particular setup with us. So why we are using this vacuum bagging technique? If you see the composites used for automotive components, or you say the windmill blade or aerospace component, जो भी windmill है वहाँ पर wind का blade है या windmill का blade है. So there we are using vacuum bagging technique. Why? Because of that particular technique, you can remove the voids to the greater extent, but you cannot get composite with 100% free of void. There will be certain voids because of the and then that depends upon the how much is the dimensions of the composite, how dimensions, as well as what type of reinforcement you are having in that particular composite material, whether it is in the fiber form or whether is it in the fabric form. But fabrics are of different types. For example, whether is it a oven fabric or whether it is a randomly oriented glass mat, or whether it is a 3D fabric, right? So based on that also the void content will vary when you produce the composite with the vacuum bagging technique. But again, in comparison to your other techniques, for example compression molding, you will get lesser voids in case of your vacuum bagging technique. So the next problem is so let me tell you the next problem associated with the composite materials. So is there any doubt in this particular discussion? और आपके पास कोई भी क्वेरी भी है वो भी आप बीच में पूछ सकते हैं मुझे, रोक के कोई प्रॉब्लम नहीं, सो दैट ये सेशन थोड़ा सा इंटरेक्टिव हो जाएगा, राइट? तो दूसरा प्रॉब्लम है हमारे कंपोजिट मटेरियल के साथ, वो है डीलैमिनेशन का. आप सभी लोगों को पता होगा डीलैमिनेशन, आप सभी लोगों ने पढ़ा भी होगा और एक्सपेरिमेंट भी किया होगा, आपने देखा होगा. सो लेट्स से सपोज दिस इज द कंपोजिट मटेरियल आई एम हैविंग, राइट. सो इफ यू लुक एट दिस पर्टिकुलर कंपोजिट मटेरियल, ये आपको बहुत ही अच्छा दिख रहा है यहाँ पर, लेकिन जब हम इसका टेंसाइल टेस्टिंग कर रहे हैं या इम्पैक्ट टेस्टिंग कर रहे हैं या बेंडिंग कर रहे हैं, व्हाट इज हैपनिंग इज दैट डीलैमिनेट हो रहा है, क्योंकि ये लैमिनेटेड कंपोजिट है वेयर वी हैव स्टैक्ड टुगेदर अराउंड 6-7 layers, right? And you see that this is the composite failed under tensile loading. You see the delamination. Why this delamination occurs? Because simply the ये जो सारे reinforcement के layers है, they are stick together because of the matrix material, right? Because of the matrix material only, and definitely under loading, the what will happen is that if efficiently you are, even though your stress is transferred from the matrix to the reinforcement efficiently, the individual layers will carry load individually, right? And how much is the distance? If you look at the center of the moment of inertia effect will be there, that you are applying load like this on this particular material, but from this center, the layers which are away from this particular center will take load differently. The layers which are at the center will take load differently. And that is the reason why these delamination, that is one of the reasons why delamination occurs, because your individual layers are taking load differently. So how to then mitigate this particular problem of the composite material? So and you see that one more important thing is that majority of the composite materials today produced are laminate composite. You take example of the composite materials used in aerospace, or maybe in the ship, or maybe in the this windmill blade, or for example automotive components. So they are or the railway components. In the railways also a lot of composite materials are used today, and this delamination problem occurs, especially in case of any type of load. So how to mitigate this particular problem? So for this particular problem, to solve this particular problem, I would like to show you one. So this problem can be solved using this 3D fabrics. You know about 3D fabrics? 3D fabrics के बारे में आपको पता है कुछ? No sir. ठीक है, मैं बता देता हूँ. So let me show you. So 3D fabrics क्या होता है? 3D fabrics are the fabrics having, the normal fabrics has length and width. It has also thickness, right? But the thickness of this particular normal 2D fabric is maximum 2 times the yarn thickness, because you have yarn in X direction, Y direction, and this thickness will be maximum 2 times the yarn thickness. But why we call this particular fabric as 3D? Because it has length dimension, width dimension, as well as thickness dimension, and thickness dimension is multiple times than the multiple times of your yarn thickness. So yarn, you understand yarn? Yarn means धागा, right? जो धागा है उसको हम yarn कहते हैं. So in this
minimum thickness means double the width of the yarn.
Yes.
That's a minimum or a maximum?
Yeah, maximum. Right.
Maximum. 2 times.
So maximum thickness will be 2 times your yarn thickness in this case. But in case of your 3D fabrics, you see that your thickness will be multiple times of your yarn thickness, and you can produce 3D fabrics of desired thickness depending upon जो भी आपका required thickness है for particular application. We know that if you want to produce laminated composite out of this simple single layer, normal 2D fabric. So if you want to produce, let's say 1 centimeter thickness, so based on what is the thickness of your single layer, you have to take a number of layers of this particular thing. In case of 3D fabric, what you can do is, here also if you want to have, let's say 1 centimeter thickness, so you can take number of layers. And you can produce the 3D fabrics. 3D fabrics, the classification of 3D, if you look at the 3D fabrics itself is a very huge, you can say, a group of material, a very huge group of materials. And in 3D fabrics, these are the 3D solid structures. This is the 3D solid structure, and let me show you that in this 3D solid structure, so we can have 3 different type of 3D solid structures. So you have this 3D orthogonal structure. 3D orthogonal का मतलब है कि all the layers so all the three sets of yarns in this particular fabric are perpendicular to each other. Orthogonal means perpendicular to each other, right? 90 degree. So you have three sets of yarn. For example, you see in this particular fabric, you have two sets of yarn. One set is vertical sets of yarn and another is horizontal set of yarn, right? Only two set of yarns. But here in case of 3D fabric, you have three sets. One is vertical, another is horizontal, and the third one is the through the thickness, which is binding these layers together. So one is horizontal, one is vertical, and the third one, which is a binder, binding these multiple layers together.
So it's not one and one, it's actually multiple in horizontal and vertical, and they are binded by
the binder, right? So you have, but again, one more thing. So this is the one type of a 3D solid structure, that is 3D orthogonal. You can have angle interlock structure where the binder yarn, so here in orthogonal your binder yarn is 90 degree. Means all the yarns in this particular structure are 90 degree. And particularly this classification is, if you look at this, so you will see that the binder is making 90 degree here also. In case of angle interlock, your binder is going through the structure at certain angle. So that's why we call it as a angle interlock structure. And third is the layer to layer interlock. So where the different layers are interlaced with each other, right? So they are attached to each other, and this is integral structure, integrated structure, integrally woven structure, means you cannot separate these layers. So if you make a composite out of this particular structure, composite reinforced with this particular structure, it will be, since it is an integrally woven structure, so there will be no delamination at all in this particular structure. There will be no delamination. So when you apply any type of load, maybe tensile, impact or bending load, it will not delaminate.
White may also be reduced in this form.
No, this is again questionable, because why? If you look at the structure, how the structure is developed, that is very much is how you are designing that particular structure is crucial in this particular case. In case of your laminates also, let's say this is the twill woven structure, it is a twill view. You can have another structure, that is this is the structure we have developed. This is the hybrid structure. This is a jute and jute glass hybrid structure. This is the plain view structure. Now the thickness of the structure that you get in different views is different. The other thing is that if you are producing, let's say, composite using vacuum bagging technique, or let's say a compression molding technique, so what will happen, you must be aware about the resin rich areas in the composite. आपको पता है resin rich area. So composite material, let's say मैंने एक composite material बनाया for example, ठीक है. So what happens is that what I ideally expect is that at every place, let's say मैंने यहाँ पे 5 mm by 5 mm कट किया है यहाँ पे हर एक जगह पे, at every place the fiber volume fraction should be uniform, right, throughout the composite. But what happens is that if I am changing the view structure, my and let's say I am using let's say same fabric I am using in compression molding, same fabric I am using in vacuum bagging and producing same composite material, right, with same fiber volume fraction. But since your view structure is different, it will lead to variation in the fiber volume fraction at the micro level. So at some places where you are having the floats, it may lead to the formation of the resin rich areas. So here also, in this case also, in this 3D fabric also, so in case of this orthogonal structure especially, here in between the layers you will get a resin rich areas. They are micro areas, dimensions less than around 1 mm or less than 1 mm dimension, but still you will get some at the micro level variation in the fiber volume fraction, and this resin rich areas again are stress concentration areas. This because you must be aware, once you understand the mechanics of the composite material under loading, you can understand the problem of the resin rich area, that it will be a stress concentration point and where the failure will start, right?
Also kind of defects.
Yes, we should have uniform fiber volume fraction throughout the composite structure, but certain faults we cannot avoid, right? Certain things we can avoid, but we cannot avoid all the problems. There will be certain problems and we have to work with that, and we have to develop a composite with we can say a desired factor of safety, so that that particular structure will work in real life. For example, your windmill blade, for example, your automotive components, or for example, the wing of the aeroplane. So you look at this particular structure. This is the 3D woven, orthogonal woven jute fabric, right? Here is your plain woven fabric. Here is your plain woven fabric, single layer plain woven fabric, right? And this is the 3D orthogonally woven fabric structure. So in this particular structure, let's say this is the for example, let's say 8 or 9 mm thickness, for example, you have, and to produce this much thickness, I need to use multiple layers of this particular. But if you look at this, since this is the integrally woven structure, the failure modes will be different. It will be a maximum load compared to your laminate, and since the failure mode is different, so the life of the composite material in this case it will be more than your laminated composite.
Is the inner house prepared? Or
Yes, this is inner house prepared. Yes. So we have the setup here and we prepared by our own. If you look at the national level and international level, manufacturing this 3D fabric, you do not have any commercial look. Only in 1 or 2 industries they are commercially manufacturing these 3D fabrics. So we are again fabricating one 3D weaving machine here. We have DST funded projects, so in that we are fabricating 3D weaving machine, which will be of commercial scale. So this is the one of the problem. It is the delamination problem. The second thing I would like to show you. So in case of this is the sandwich structure, right? So this sandwich structure is again a composite sandwich structure, and you know the sandwich structures are used for multiple applications, right? Specifically for energy absorption के लिए हम इसको use करते हैं at various applications. And this particular sandwich structure, if you look at here, what we have done is, what is done here is that different layers are sticked together, right? First, you have this corrugated layer, so you can have corrugation of any dimension, any shape based on your requirement. So you can have triangular shape, right? You can have rectangle, or you can have hexagon, right? And what is there is that after making this corrugated structure, it is stacked together to according to the desired thickness, how much thickness you need. So based on that, it is stacked together, and simply it is sticked by resin. So this type of, again, this is the one of the good composite material, good sandwich composite material, which can also bear good amount of load. But what is the problem again associated with this particular composite? Delamination again, because it is sticked only with the help of your epoxy resin. तो ये क्या होगा, जब आप इसके ऊपर कोई भी लोड आएगा, चाहे वो फ्लेक्चुरल लोड हो या इम्पैक्ट लोड हो या टेंसाइल, तो नॉट, बिकॉज उसका एप्लीकेशन ही अलग है, जहाँ पे फ्लेक्चुरल और इम्पैक्ट लोड ही आएगा या कॉम्प्रेसिव लोड आएगा. So efficient energy transfer तभी होगा जब यहाँ पर the you can say the bonding between these layers is proper, and since it is sticked by the matrix material, so it will not bear the load, as much load as compared to your integrally woven preforms. So let me show you the integrally woven preforms. So you look at these particular structures. Look at these particular structures. These are the hollow structures, and these are integrally woven structures. जब आप उसको वीविंग मशीन पे बनाते हैं तो ये ऐसे बन के आता है ये कपड़ा सीधा. Whereas in this case you see that ये तो चिपका हुआ है. It is sticked by using the epoxy matrix or any other binder. But here, this particular fabrics, if you look at, these are integrally woven structures. You can weave these structures and you can produce different shapes. And we have prepared it already, and we have produced these particular structures. And we can have different cross-sectional shapes. You can have triangular profile, we can have trapezoidal profile, rectangular, or any other profile. Any other means the shape we can have here. And what is the advantage of this integrally woven structure? Again, the load transfer will be more efficient. So there will be no delamination. And to produce this structure, you need a strong knowledge of the weaving technology, of fabric manufacturing technology. And these structures are also nobody produces in India, right? So you look at this particular. This is the honeycomb structure, hexagon. You can get. So we have again produced this particular structure using weaving technology. And you can get directly on the weaving machine itself, you will get a fabric like this, and you simply have to insert the mold into this particular hollow channels, and using vacuum bagging technique we can produce the composite material. So let me show you one more thing here.
This technology or this machinery is available with the department?
It is not available here. I have produced it in IIT Delhi. So IIT Delhi. But here I am, as I said you that I am developing one 3D weaving machine here, where we will be able to produce 3D fabrics with different thickness. We can produce 3D fabrics with this type of spacer structures and the composite materials. So this is the spacer fabric, and this is the composite material of this particular spacer fabric. So the weaving technologies. Let me show you one more important thing. So you know this profile weaving, profile structures. So this is again, let me show you why we use these profile structures. You see this particular structure. So ये भी structure जो है ये हम जब weaving machine पे बनाते हैं तो उसी shape में आता है. You can produce structure of any shape. So this is the profile, pie profile. So we have produced it by our own hand on handloom. So why these profile structures are produced? If you look at aerospace composites, if you look at the automotive composites or any other composite material where you need to join the composite components, right? So in that case, what is generally done is, for composite joining, what is done is, we can have riveting, or we can fastener, you can use fastener also, there is no problem. But what happens is that the junction, this is the junction, right, where this ये जो surface है and this part is joined together, right, using this particular material here, and here you have fastener. Now what happens is that, let's say you have a composite material and you want to join this composite material. So you can use a fastener, there is no problem. So let's say for example this is the T profile, and let's say I want to join some component here and some component here, we can use the fastener, there is no problem. But what happens is that the problem occurs at this particular junction. How much is the load taken by the junction, and there actually this particular composite material this particular joints fails, right? Because junction is the stress concentration point in this particular type of you can say joints. So if you look at this particular, so this is how this particular profile structures view. Actually, if I explain it, it will be difficult for you to understand because your background is completely different, I can understand. But let me tell you that this is a special technique to produce such type of profiles, right? So where we have produced by our own hand different type of profiles. U profile, plus profile, L profile, blade profile, you can have, and their composites, and we have also produced the profiles by stitching also. So this is the integrally woven profile, this is the stitched profile, this is the integrally woven U profile, this is the stitched profile, where this 1, 2, 3 fabrics are stitched together here. This is the stitched blade profile, this is integrally woven, this is again integrally woven, this is stitched profile, and composites of these all are produced. And we have tested it for the junction strength. What will happen to the composite at the junction? You look at this, for the stitched composite, the composite fails only at the stitch line, because there only it is the different layers are held together by the stitching only, the stitching thread only. But if you have the integrally woven structure, it will fail due to the fracture of the yarns. And this particular integrally woven structure will bear more load, much more load at the junction than your stitched profile. And this technique is again, let me tell you that this is again a very special technique, and for this again you need a in-depth information or knowledge about the weaving technology. And these preforms are also not available commercially in India, but they are available in some other countries. And we are in India, we are trying to develop these structures also, profile structures. So one of my PhD students, he will be working on these particular profile structures, but we have developed another technique for producing these particular profiles and their composite materials. If you are interested, you please register for that particular course, specifically for the 3D fabrics. So this is the one that is the delamination, and I have shown you, if you change simply the preform structure, you can avoid certain problems, you can get enhanced mechanical performance, desired mechanical performance. Third problem है हमारे composite materials में, वो है that is the health monitoring of the composite materials. Suppose for example you have a composite material, let's say windmill blade you have, right? 40 feet का windmill blade है यहाँ पर और वो rotate कर रहा है, let's say for last 1 year, and you don't know that इस windmill blade में हो या आप एरोप्लेन का ब्लेड हो या कोई भी दूसरा ऑटोमोटिव कंपोजिट है या लेट्स से सुपर स्ट्रक्चर जो शिप है, शिप का जो सुपर स्ट्रक्चर है वहाँ पर ऑफ दिस पर्टिकुलर कंपोजिट मटेरियल, यू कैन अंडरस्टैंड, यू कैन observe the you can say the damage that is happening at the surface, but what is happening at the inside of this particular structure we cannot get. And it has been already reported many of the failures of the such composite material catastrophic failure of the composite material because of non-detection of these particular defects in the composite material. So for example, defects क्या हो सकते हैं यहाँ पर? Micro cracks. So for example, let's say this is the jute epoxy composite material. Or maybe you have glass epoxy composite material, or you have carbon epoxy composite material, and it is used in the let's say aeroplane wing, right? Or you have this. So for example, this is the strain monitoring sensors. So we have glass fabric as a substrate, and on this particular glass fabric we have developed one recipe using this graphene based materials. And since we know the graphene is conductive, graphene based materials are conductive in nature, so this particular material will become a sensor, and we embed this particular sensor in the composite materials and try to measure the change in the resistance under the deformation. So we expose this particular material occur, and that we are trying to correlate that particular change in the resistance with the deformation in the particular composite material, and try to develop a sensor which can be calibrated, type of a sensor which can be calibrated and which can be used in composite structures, a huge composite structures. For example, you have, let's say, windmill blade ho, yeah, for example, unmanned air vehicles which are specifically used for surveillance purpose, right? For example, you have again various aeroplane.
devices भी होना चाहिए उसका.
Of course, yes, absolutely right. होना चाहिए. Composite at the outer layer or at the edges, again on the top side as well as at the edges also. So it is different. If you look at the composition, it is from the composition point of view, it is different. This is not like a normal glass. But if you see the composition wise, definitely if you look at the chemistry of the fibers, or if you look at the requirement of any polymer to produce a fiber, so there are certain requirements. So otherwise we cannot produce filaments or textile fibers from any polymer. Okay, so 3D printing, 3D viewing are completely different. So they are completely different. So relating 3D viewing and 3D printing is, from my point of view, it is completely we cannot relate.
But sir, आजकल 3D printing में continuous fiber 3D printing भी आ रहा है.
Yes, continuous fiber. Your question is very right. We can use textile-based fiber, right, filament, and we can imprint it with the matrix, and we can put in any shape, right? But that is different. That the technique is different. What is the problem with that particular technique? Is, let me tell you. If you look at the structure, that structure is not interlaced type of structure. In case of weaving, it is an interlacement. It is interlacement of yarns. So the structure is different. And in case of 3D weaving, you see that it is an integrally woven structure. It is a one structure, entirely one structure, and there is no stitching or something like that. In case of 3D printing, you are simply laying the filament impregnated with the matrix in different shape. But if you look at the deformation behavior of this particular composite material, let's say 3D woven composite and 3D printing, it will be completely different. So because you know that if you, that's why I'm saying you that अगर आपको deformation behavior, or in the other words मैं बताऊंगा, if you understand the mechanics of the composite material under different loading conditions, you can easily understand which composite material will give you more mechanical performance. So that for that particular thing, you should understand how your composite will be deformed under various loading conditions.
A study is published in glass fiber for DLP assisted printing. They are increasing the mechanical strength.
But we have to compare. We should compare what is happening. Look, what happens is that study of the composite material is one thing, and when we are looking at the application point of view, when we are trying to implement in a real application, for example, let it be any, let's say aerospace component or maybe windmill blade, how that component is behaving in that particular conditions, and how it is failing in that particular condition, how it is taking the load, how long it will be, it can be used for that particular application. I mean the life of the composite material. We have to look at these particular things. So एक चीज़ मेरे को बताना है आपको, that is the last again one point, that is the problem, the problem of the composite material, that is the effect of environmental conditions. For example, let's say temperature, or let's say the moisture, or maybe the UV, right? So that is again if you look at the
कुछ और रिएक्ट करती हैं, और अगर हायर टेम्परेचर जैसे समर्स में ज़्यादा डिफरेंट बिहेव करने लगती हैं, तो इनकी ये भी टेस्टिंग सर चेक की जाती है.
Yes, we can do it, because you know when you are using these composite materials, when you, for example, you are using in the windmill blade, so you know that aeroplane generally flies at the height of 35,000 feet, where the temperature is in the minus 50 degree, minus 40 about it. So in that case, in that particular conditions, your composite should be composite should sustain that particular environmental conditions, right? So definitely we have to test it. If you, for example, the satellites, many satellite components are the composite materials. So when they are going in the space, so again the environment is completely different. So for that you have to do the test according to that particular environment, so that that component will sustain in that environment. Definitely we have to do that. For example, your composite is used in the ship, superstructure of ship, where the environment is different. Your composite may experience humidity. Your composite experience the seawater, right? Salts. So the composite again you have to test for that particular environment, so that it will sustain the in the real life application.
So in the 3D fabric that you shown, I think the binder is the main component that prevents the delamination of the layers. And in the normal composite, the bonding strength between the matrix and the reinforcement, that is the that prevents the delamination. So can the single binder can withstand that much of shear load that causes the delamination, or the matrix, the resin that we use, that also has some load?
Okay, good question. So for that you have to observe this 3D fabric. If you look at it, it is not like only one binder. It is not only one binder. There are multiple binders across the width of the fabric. Across the width of the fabric. And if you look at the different layers in this particular structure, you will understand that the horizontal layers and vertical layers, they are like this. Right? They are like this. And the binder is again binding these particular layers together. So it is not the one binder, right? So in that particular diagram, it was the unit cell of that particular structure where only one binder was shown. But if you look at the structure throughout the width, we can have multiple number of binders, and based on number of binders, we have already done one study that when you change the number of binders, the impact energy absorption of the composite material changes. Right? More the number of binders, the impact energy absorption will be more. And one more thing is that in case of this orthogonal structure, the stiffness of this orthogonal structure is very much high compared to your angle interlock and warp interlock structure. So for example, if you want to produce a composite material where the shape is, let's say, a curvy shape, for example. So in that particular shapes, you should not use 3D over orthogonal structure. You should use angle interlock structure or warp interlock structure, which is more flexible compared to your orthogonal structure, and which will give you more flexibility during the manufacturing of the composite material. Right? If you look at this particular structure, it is highly stiff.
Yes.
So if I want to produce a curved shapes, it is very difficult. Right? But if I use this angle interlock structure or warp interlock structure, they are more flexible, and you can use it in a for such complicated shapes or maybe some curves. Right? So any other doubt we can discuss. We have produced here
Orthogonal.
orthogonal structure, 3D over orthogonal using jute yarn. This is the jute yarn.
So yeah, just I'm curious to ask. We have carbon composites. We have multiple directions. We use it in that. So is there that provision? Can we customize this kind of a weaving where we can have multiple directional weave, which is possible? So now it is a 3-directional weave. So like there is like fourth direction or a 5th direction which will come is other than the 3rd directions. So which is
There is a confusion. 3-dimensional fabric doesn't mean yarns in 3 directions. 3 dimensions means it has 3 dimensions: length dimension, width dimension, and thickness dimension. In case of, I got your point. In case of, you mean to say that can we have yarns reinforcement in multiple directions, any other direction, and it is an integrally woven structure at the same time? Is it that? So we can have this particular structure, and these structures are commercially produced, where multiple layers of yarns in, let's say, 0 direction, multiple layers in the 90 direction, multiple layers at bias angle, let's say 45 angle, they are laid and they are stitched together using needles, and these structures are commercially produced. They are in the production and they are used in variety of applications, and windmill blade is one of that.
Sir, what type of testing generally we followed in the textile? Generally, for example, in the mechanical materials testing and non-destructive testing or some destructive testing are followed, ultrasonic testing, vibration testing. In the textile, which type of testing is?
For textile materials or composite materials?
For composite materials.
Achha.
Which type of
For
testing?
the composite material, again, we can have tensile testing, 3-point bending or 4-point bending test, compression test. If you have such sandwich composites, we can have a compression test. Again, for the sandwich, we can perform the bending test, impact test. So for such laminated composite or 3D fabric reinforced composites, we can have impact test. For example, you can have Charpy impact or Izod impact. So this is the in-plane impact test, Charpy and Izod. You can have out-of-plane impact test also, that is drop weight impact. So you can have a drop weight impact. Again, you can have a static or you can have a dynamic impact test.
Is there any non-destructive type testing is here like ultrasonic testing, vibration testing?
No, it is not there. It is in,
so that we can recognize the internal cracks and voids.
Right. So for that you have to do the micro-CT scanning. Micro-CT scanning is one of the non-destructive tests performed to understand the internal structure of the composite material. Let's say after testing also you can find out what has happened in the internal structure, or before also to identify the voids. And micro-CT scanners are widely used, and they are available in India. It is available in IIT Delhi also. It is available. Micro-CT scanning is one of the non-destructive tests we carry out, and generally for all these aerospace components, micro-CT scanning is done to identify any void in the structure.